Hello there, and welcome to Science for Sleep, where curiosity settles in softly and the universe unfolds at a pace that never asks you to hurry. Tonight, you and I are going to wander through one of the biggest questions the cosmos can offer, not with rushing footsteps or flashing headlines, but with slow, steady steps that let each idea rest for a moment before moving on. We're going to talk about something so large, so heavy, and so quietly powerful that it shapes entire galaxies without ever making a sound. We're going to explore the largest black hole ever discovered and the long, patient story behind how something like that can even exist. Before we drift too far into that deep, distant place, let me ask you something simple and very close to home. Where are you listening from right now? Are you curled up in bed, sitting in a quiet room, or maybe letting this play in the background while the world outside your window slowly grows darker or lighter? And what time is it for you in your little corner of the planet at this exact moment? It is always interesting, isn't it, to think about how we can all be here together, scattered across different hours of the day and night, yet sharing the same gentle stream of words and ideas. If you find this space calm or curious, or just a pleasant way to unwind, you might consider giving the video a like or subscribing to the channel. It helps this small pocket of quiet science find others who might be looking for something thoughtful and unhurried at the end of their day. There is no pressure, of course. You're welcome to simply listen, breathe, and let the ideas pass by like slow-moving clouds. Now, let us begin easing into our topic, because when people hear the words largest black hole, the mind often jumps straight to something dramatic. You might imagine a swirling vortex, a violent storm of light and matter being torn apart, or a kind of cosmic vacuum cleaner racing across space. The reality is far stranger, and in many ways, far calmer. The largest black holes in the universe are not wild, roaming monsters. They sit, mostly still, at the centres of galaxies, including our own. They are quiet anchors, holding vast systems of stars in place with their immense gravity. To understand what it means for a black hole to be the largest ever discovered, it helps to take a step back and think about what large really means on a cosmic scale. On Earth, we're used to measuring things in meters, kilometers, maybe the size of a city or a mountain. Even when we think about space, we often talk in terms of planets and stars, which already stretch our sense of size beyond everyday experience. But black holes, especially the biggest ones, operate on a scale that makes even stars feel small by comparison. When astronomers talk about the size of a black hole, they are not usually talking about a solid object with a surface you could, in theory, land on. A black hole does not have a surface in the normal sense. Instead, it has a boundary called an event horizon. This is the invisible line around the black hole where gravity becomes so strong that nothing, not even light, can escape. The size of a black hole is often described by the size of this event horizon. The more massive the black hole, the larger this invisible boundary becomes. So when we say the largest black hole ever discovered, what we really mean is the one with the greatest mass, and as a result the widest event horizon that we've been able to identify so far. And identifying it is not simple. Black holes do not shine, they do not reflect light, they reveal themselves only through their influence on the space and matter around them. In a way, astronomers are like detectives, looking for clues left behind by something they cannot see directly. Imagine standing in a dark room where you cannot see an object in the centre. You might still be able to tell it is there by the way the floor slopes toward it, or how objects you roll across the ground curve toward a single point. In space, stars and gas clouds play the role of those rolling objects. Their paths bend, their speeds change, and their light shifts in ways that reveal the presence of an enormous gravitational source. Now, as we settle into this idea, picture a galaxy, not just as a flat image in a book, but as a vast three-dimensional structure made of hundreds of billions of stars, clouds of gas and dust, and dark matter that we still barely understand. At the centre of most large galaxies there is a supermassive black hole. These are not formed from the collapse of a single star. Instead, they grow over billions of years, gathering mass through mergers with other black holes and by pulling in matter from their surroundings. Some of these supermassive black holes weigh millions of times more than our Sun. Others weigh billions of times more, and then there are a few that go even beyond that, pushing into a range that makes scientists pause and double-check their measurements. As you listen to this, you might find yourself wondering how something can grow that big in a universe that, while vast, still follows certain rules. After all, gravity is powerful, but it also works slowly over great distances. For a black hole to become the largest known, it needs time, material, and the right environment. It needs to be in a place where galaxies collide, where streams of gas flow inward, and where smaller black holes can merge to form something greater. One of the fascinating things about the largest black holes is that they are often found in the centres of very old, very large galaxies, especially those that sit in crowded regions of the universe known as galaxy clusters. These are places where hundreds or even thousands of galaxies are bound together by gravity, slowly interacting and sometimes merging over cosmic timescales. When two galaxies collide, their central black holes do not immediately crash into each other. Instead, they begin a long, slow dance, spiraling closer over millions or billions of years. As they draw near, they disturb the surrounding stars and gas, sending waves of matter toward the centre. Eventually, the two black holes merge, releasing an enormous amount of energy in the form of gravitational waves, ripples in space itself that we can now detect here on Earth with sensitive instruments. Each merger adds to the mass of the growing black hole. Over time, through repeated collisions and steady feeding on surrounding material, a black hole can become truly enormous. Now, let us bring this closer to the question that sits at the heart of our quiet exploration tonight. Which black hole is the largest we have discovered so far? At the time of this recording, one of the leading candidates holds a title that is both technical and a little poetic. It is known as TON 618. The name itself does not sound very dramatic, but what it represents certainly is. TON 618 is a quasar, which means it is a supermassive black hole that is actively feeding on a vast amount of matter. As gas and dust fall toward it, they form a bright spinning disk around the black hole, heating up and glowing intensely. This light can travel across billions of light years, making the quasar visible to us even from the far edges of the observable universe. The black hole at the heart of TON 618 is estimated to have a mass of around 66 billion times that of our Sun. Let that number sit for a moment. Our Sun is already massive enough to hold 8 planets, countless smaller objects, and a vast cloud of distant icy bodies in its gravitational grip. Multiply that by 66 billion, and you start to approach the scale of what we're talking about. If you were to replace our Sun with this black hole, its event horizon would extend far beyond the orbit of Neptune. In fact, it would reach out to distances comparable to the outer regions of our solar system. And yet, despite this enormous size, it would still be only a tiny point compared to the full width of a galaxy, which can span hundreds of thousands of light years. There is something quietly humbling about that contrast. The largest black hole we know of is unimaginably big on a human scale, and yet, in the grand structure of the universe, it is still just one component in a much larger system. TON 618 is located more than 10 billion light-years away from Earth. That means the light we see from it today began its journey when the universe was much younger than it is now. In a sense, we're not seeing it as it is, but as it was, long before our planet even formed. When astronomers study objects like this, they are not just learning about black holes. They're also learning about the early universe, about how quickly massive structures formed, and about the conditions that allowed such enormous concentrations of matter to come together in the first place. It raises gentle, lingering questions. How did something so massive grow so quickly in cosmic terms? Were there special conditions in the early universe that made this possible? Or are there even larger black holes out there, hidden in regions we have not yet been able to study in detail? As technology improves, and as new telescopes come online, astronomers continue to scan the sky for distant quasars and other signs of extreme black holes. Each discovery adds another piece to the puzzle, another data point in the long story of how structure emerges in the universe. Now, as we ease through these ideas, it might be helpful to think about how we actually measure something like the mass of a black hole that is billions of light years away. After all, we cannot put it on a scale. We cannot send a probe to orbit it. We rely instead on light, motion, and the way gravity shapes its surroundings. One method involves studying the speed of gas and stars near the centre of a galaxy. The faster they move, the stronger the gravitational pull must be. By measuring these speeds and applying the laws of physics, astronomers can estimate the mass of the object causing that motion. In the case of distant quasars, another technique comes into play. The light from the glowing disk of matter around the black hole can be spread out into a spectrum, revealing subtle shifts in wavelength. These shifts tell scientists how fast the gas is moving and how far it is from the centre. From this they can infer the mass of the black hole itself. These measurements are not perfect. They come with uncertainties, margins of error and assumptions. That is why the title of largest black hole ever discovered is not a permanent one. It is more like a placeholder, waiting to be updated as our view of the universe becomes clearer and more detailed. There is a quiet excitement in that idea. Somewhere out there, perhaps in a region of space we have not yet explored, there may be an even larger black hole, quietly shaping its surroundings, waiting to be noticed by a telescope on a small planet orbiting an ordinary star. A region of space where gravity has become so strong that it changes the rules, where mass, light, and even time behave differently. And at the centre of it all, not a roaring engine or a blazing fire, but a quiet, dark presence that simply exists, shaping everything around it through its weight alone. What does it really mean for something to be large in a universe that seems to have no obvious edge? And what does it mean for something to be dark in a place filled with light from billions of stars? You might notice that when people talk about the biggest things in existence, they often reach for familiar comparisons. They say things like, "This galaxy is so wide it would take light thousands of years to cross," or "This black hole could swallow our entire solar system." These comparisons are helpful, but they also quietly remind us of how limited our everyday sense of scale really is. Our lives unfold in rooms, streets, neighbourhoods, and maybe cities. Even the largest landscapes we visit, mountains, oceans, wide plains, still fit comfortably inside a single planet. The universe, on the other hand, does not seem to notice our preference for neat, manageable sizes. When you first hear about something like a black hole that is tens of billions of times more massive than the Sun, the number itself can feel almost decorative. It is so far beyond ordinary experience that it loses its sharpness. It becomes a kind of soft, rounded idea rather than a precise measurement. And maybe that is not such a bad thing. Maybe part of the wonder is letting the mind stretch a little, even if it never quite reaches all the way. Darkness, too, is an interesting word in this context. On Earth, darkness usually means the absence of light. It is what happens when the sun sets or when you turn off a lamp. It is something that comes and goes, something that can be chased away with a switch or a candle. The darkness of a black hole is different. It is not just a lack of light. It is a place where light itself cannot leave once it has crossed a certain boundary. That gives it a different quality, not just empty, but sealed. If you think about it for a moment, that idea alone is already enough to pause over. Light is the fastest thing we know in the universe. It is the ultimate messenger, carrying information across space, telling us what stars are made of, how far away galaxies are, and what happened billions of years ago. And yet, there are places where even this tireless traveller cannot escape. That boundary, the event horizon, is like a quiet line drawn in space, beyond which stories cannot be told to the outside world. But even here, in this place of extreme gravity and sealed-off regions, there is a kind of balance. Black holes do not simply erase everything around them. In fact, most of the time, they sit at the centres of galaxies, surrounded by vast, glowing structures of stars and gas. The darkness is nested inside light, and the two coexist in a way that shapes the entire system. As you listen, you might find yourself picturing a black hole as a hole in the universe, a literal gap or tear. That image is common, and it is not entirely wrong, but it can also be a little misleading. A black hole is not a hole in the sense of an empty space. It is more like an extremely dense region, where a great deal of mass has been packed into a very small volume. The gravity is not coming from a void, it is coming from something that is very much there, even if we cannot see it directly. This brings us back to the idea of size. When we talk about the largest black hole, we're really talking about mass and influence rather than physical width, in the usual sense. The event horizon gives us a kind of size we can picture, but the true reach of a black hole extends far beyond that. Its gravity shapes the motion of stars, the flow of gas, and even the structure of the galaxy itself. Imagine a city built around a central landmark, a mountain, a river, or a wide plaza. Streets, buildings, and neighbourhoods grow in response to that feature. Over time, the entire layout of the city reflects its presence. In a similar way, galaxies grow and evolve around their central black holes. The largest black holes are often found in the largest galaxies, and the two seem to develop together, each influencing the other's growth. This connection between size and darkness, between the visible and the invisible, is one of the reasons black holes have such a strong pull on our imagination. They sit at the meeting point of what we can observe and what we can only infer. We see stars moving faster than they should, gas heating up and glowing as it spirals inward, light bending as it passes by. From these clues, we build a picture of something we cannot look at directly, and yet, for all the advanced instruments and careful measurements, there is still room for a sense of wonder that feels almost old-fashioned. The largest black holes are not just data points in a catalogue. They are reminders that the universe is capable of building structures far beyond anything we can create or fully grasp. It is also worth noticing how our language changes when we talk about these things. We use words like monster, giant, and cosmic behemoth. These are human words, borrowed from stories and myths, applied to objects that exist entirely outside of human experience. In doing so, we're not just describing what we see, we're also expressing how it makes us feel. That feeling is not always fear, though fear does play a role. There is also a sense of fascination, of being drawn towards something that challenges the limits of what we know. The largest black hole ever discovered is not a threat to us. It is far too distant for its gravity to have any effect on our galaxy, but it still captures our attention simply because of what it represents. As we continue, let us take a moment to think about how black holes fit into the larger story of the universe. They are not isolated oddities. They are part of a broader pattern of structure and change. The universe began in a hot, dense state, expanded, cooled, and over time matter clumped together under the pull of gravity. First came simple particles, then atoms, then clouds of gas, then stars and galaxies. Black holes emerged as part of this process, not as exceptions, but as natural outcomes of gravity doing what it does best. In the early universe, conditions were different. Matter was more evenly spread out, and the first stars were likely much larger and more massive than most stars we see today. When these early giants reached the end of their lives, they collapsed, leaving behind black holes that were already larger than the ones formed by most modern stars. These early black holes may have served as seeds, growing over time into the supermassive and even ultramassive black holes we observe now. This idea, that something so extreme can grow from relatively ordinary beginnings, adds another layer to the sense of wonder. It suggests that the largest black holes are not just products of rare special events, but the results of long, patient processes playing out over billions of years. There is a quiet comfort in that if you think about it. The universe does not always rush. It builds its most impressive structures slowly through countless small steps and interactions. Gas drifts in, stars form and die, galaxies merge, black holes spiral together. Each event on its own might seem unremarkable on a cosmic scale, but together they create something truly enormous. Now let us turn our attention back to the idea of darkness, not just as a physical property, but as a kind of conceptual space. When scientists talk about what happens inside a black hole, their equations begin to reach their limits. The known laws of physics, which work so well for describing planets, stars, and even the expansion of the universe, start to break down near the centre of a black hole. This region, often called a singularity, is where density and gravity are thought to become infinite, or at least so extreme that our current theories cannot handle them. It is important to say that this does not necessarily mean there is literally a point of infinite density sitting inside every black hole. It means that our models stop being reliable in that regime. The singularity is as much a sign of the limits of our understanding as it is a description of a physical object. In that sense, the darkness of a black hole is also a kind of intellectual darkness. It marks a place where our knowledge fades, where we can no longer shine the light of theory and observation with the same confidence. That too can be a source of wonder rather than frustration. It reminds us that science is not just a collection of answers, but an ongoing process of asking better questions. As you listen, you might find your thoughts drifting to more personal ideas of size and darkness. Perhaps you think about moments in your own life that felt vast, a big decision, a long journey, or a period of uncertainty. In those moments, the future can feel like a kind of darkness, not because it is empty, but because it is unknown. You cannot see what lies beyond a certain point, but you still move forward, step by step, in a quiet way. That is not so different from how we approach the study of black holes. We observe, we measure, we build models, and we slowly push the boundary of what we can understand. We do not see everything at once. We learn by following the edges. Let us bring this back to the largest black hole we know about, the one at the heart of the quasar known as TON 618. When astronomers study it, they are not just impressed by its mass, they are also interested in what it tells them about the era in which it formed. The light we see from it today left its surroundings billions of years ago. That means this black hole was already enormous when the universe was relatively young. This raises questions that are still being explored. How did it grow so quickly? Were there special conditions in its region of space that allowed it to gather mass more efficiently than others? Or are we only seeing the tip of the iceberg with many similar objects waiting to be discovered? These questions tie back into the broader theme of wonder. The largest black hole is not just a record holder. It is a clue, a signpost pointing toward deeper processes at work in the universe. It hints at a story that is still being written, one that stretches from the first moments after the Big Bang to the distant future of cosmic expansion. As we move along, it might be helpful to think about how we, as listeners and observers, fit into this picture. On one level, we're incredibly small. Our planet is a tiny dot orbiting an average star in a galaxy that is one of billions. The largest black hole we know of sits billions of light years away, completely unaffected by anything we do. On another level, though, we're connected to it through the simple act of understanding. The same physical laws that govern the behaviour of that distant black hole also govern the motion of the atoms in your body, the light entering your eyes, and the sound waves carrying these words to your ears. The universe is not divided into separate realms of the very large and the very small. It is a continuous system, and we are part of it. This idea can be both grounding and expansive. Grounding because it reminds us that we are made of the same basic ingredients as stars and galaxies. expansive because it suggests that our curiosity is not out of place. When we wonder about the largest black hole, the universe is, in a sense, wondering about itself. Let us take another quiet step forward and consider how the concept of largest might change in the future. Science is not static. New telescopes, new methods, and new discoveries constantly reshape our understanding. The title of largest black hole ever discovered is not fixed. It belongs for now to the object we have measured and confirmed with the tools available to us. In the coming years, observatories like the James Webb Space Telescope and future ground-based instruments will peer deeper into space and further back in time. They may find quasars even more distant, with black holes even more massive. When that happens, the story will expand again, and our sense of scale will stretch a little further. There is something quietly reassuring about that. No matter how much we learn, there always seems to be more waiting beyond the current horizon. The universe does not run out of things to be curious about. Let your thoughts linger on the simple pairing of size and darkness. One represents something we can measure, compare, and quantify. The other represents something that resists direct observation, something that invites imagination and careful inference. Together they form a kind of balance that runs through much of science. We measure what we can. We wonder about what we cannot. And in the space between those two we find stories, questions, and a steady, patient sense of exploration. Long before anything in the universe had a name, before there were stars to shine or planets to wander, there was already a quiet rule in place, simple and persistent. Things with mass attract each other. This idea, which we now call gravity, does not announce itself with fanfare. It does not flash or roar. Most of the time it works so gently that you barely notice it. It is the reason your feet stay on the ground, the reason rain falls instead of drifting away, the reason the moon keeps its steady company with Earth night after night. Gravity, in its everyday form, feels like a polite presence. It holds things together without making a fuss. But in the deeper parts of the universe, far from the calm balance we experience on our planet, gravity has another side. Given enough mass and enough time, it stops being subtle. It stops being something that merely nudges and becomes something that dominates. It starts to win every argument, pulling harder, bending space more sharply, and eventually changing the very rules by which matter and light are allowed to behave. This is where the story of black holes truly begins, not with darkness, not with mystery, but with gravity doing what it always does, only on a scale so large that the outcome becomes something extraordinary. If you think about gravity in your daily life, it feels predictable. Drop a cup and it falls. Toss a ball and it follows a graceful arc back to the ground. These motions are easy to picture because the forces involved are small compared to the strength of the objects themselves. The Earth is massive, yes, but the cup and the ball are solid enough to remain mostly unchanged as they respond to its pull. Now, imagine a cloud of gas in space. There is no solid surface, no rigid structure, just atoms drifting, spread out over a vast region. At first, gravity barely seems to matter. The atoms move slowly, influenced by tiny pushes from radiation, nearby stars, or passing shockwaves from distant explosions. But over time, even a very weak gravitational attraction can start to add up. Some parts of the cloud might become slightly denser than others. Where there is more mass, there is a slightly stronger pull. That stronger pull draws in more gas, which increases the mass, which increases the pull even further. This is how gravity begins to tip the balance. It does not act all at once. It builds momentum, quietly and steadily. Eventually the gas cloud collapses inward, growing hotter and denser at its centre. If enough material gathers, a star is born. This process, repeated countless times across the universe, fills galaxies with points of light. Most of the time, the story ends there. The star shines for millions or billions of years, using nuclear reactions to push back against the inward pull of gravity. There is a kind of truce in place. Gravity tries to compress the star. Energy from the star's core pushes outward. The two forces balance each other and the star remains stable. But not all stars are created equal. Some are much more massive than others, and for the most massive ones, gravity never truly settles for a draw. It waits. When a very large star reaches the end of its life, it runs out of the fuel that powers those outward reactions. The push from the inside weakens. Gravity, patient as always, takes its opportunity. The star's core collapses in on itself, falling inward at a significant fraction of the speed of light. The outer layers may explode outward in a brilliant supernova, but the centre keeps shrinking. What happens next depends on how much mass remains in that core. If it is below a certain limit, it might form a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. But if the mass is higher than that, even the incredible pressure inside a neutron star is not enough to stop the collapse. At that point, gravity does something remarkable. It wins completely. The core continues to shrink, becoming denser and denser, until it crosses a threshold where the escape velocity exceeds the speed of light. This is the birth of a black hole. From that moment on, nothing inside a certain boundary can ever get out. Not particles, not radiation, not even light itself. This boundary, the event horizon, is not a physical surface you could touch. It is more like a line in the structure of space. Outside it, paths exist that lead away, back into the wider universe. Inside it, all possible paths lead inward. If you were somehow able to approach this region, you would not feel a sudden wall or barrier. You would simply reach a point where turning back becomes impossible. Now that description often brings up images of dramatic destruction, and in some cases, that is not entirely wrong. But it is also worth remembering that most black holes are not constantly devouring everything around them. Space is vast, and even near a black hole there is a lot of empty room. Objects can orbit black holes just as they orbit stars or planets, provided they keep a safe distance. The difference is what happens when something does get too close. As gas, dust, or even stars fall toward a black hole, they usually do not drop straight in. Instead, they spiral around, forming a flat, spinning structure called an accretion disk. Friction and intense gravitational forces heat this material to extreme temperatures, causing it to glow brightly. In some cases, this glowing disk can outshine the entire galaxy it sits in. This is one of the great ironies of black holes. The things themselves are dark, but the regions around them can be among the brightest places in the universe. As gravity continues to gather material, the black hole grows. Each bit of mass that crosses the event horizon adds to its total. The more massive it becomes, the larger its event horizon grows. The influence of its gravity reaches farther into space, and in environments where there is plenty of material to feed on, this growth can continue for a very long time. This is where the story begins to shift from individual stars to entire galaxies. In the centres of most large galaxies, there are supermassive black holes, weighing millions or billions of times more than the Sun. These did not form from the collapse of a single star. Instead, they grew over cosmic time, starting from smaller seed black holes and gradually adding mass through accretion and mergers. Think of a crowded dance floor, where many people are moving around in the same space. Sometimes two people bump into each other and end up moving together for a while. In the centres of galaxy clusters, entire galaxies can collide and merge. When they do, their central black holes eventually find each other and begin a slow, gravitational dance of their own. At first, they orbit at a distance, surrounded by swirling stars and gas. Over time, interactions with this surrounding matter cause them to lose energy and spiral closer. Eventually, they merge in a dramatic event that sends ripples through the fabric of space itself. These ripples, known as gravitational waves, spread outward at the speed of light, carrying information about the masses and motions involved in the collision. Each merger creates a larger black hole than either of the two originals. Over billions of years, through repeated collisions and steady feeding, some black holes grow to truly staggering sizes. Now, let us return to the phrase we started with, when gravity stops being polite and starts winning. In everyday situations, gravity is easy to ignore because other forces often dominate. The electromagnetic forces that hold atoms together are far stronger on small scales. The structural strength of materials resists compression and tension. Even the pressure of air can balance gravity in certain conditions, as in the case of a balloon or a cloud. But gravity has one unique advantage. It always adds up. There is no negative mass to cancel it out. Every bit of matter contributes to the overall pull. Over large distances and long times, this makes gravity the dominant force shaping the universe. This is why the largest structures in the cosmos, galaxies, clusters of galaxies, and the web-like patterns of matter stretching across space are all arranged by gravity. And at the deepest centres of some of these structures, gravity becomes so concentrated that it creates black holes. For the largest black holes, this process reaches an extreme. Their mass is not just the result of a single collapse, but the cumulative outcome of countless events. Each star that falls in, each cloud of gas that spirals past the point of no return, each merger with another black hole adds to the total. As the black hole grows, it can begin to influence its environment in more subtle ways as well. The energy released by the accretion disk can heat surrounding gas, sometimes pushing it away and slowing further growth. In this way, the black hole and the galaxy around it can enter into a kind of feedback loop, each affecting the evolution of the other. This relationship between gravity, growth, and balance is one of the reasons astronomers are so interested in the largest black holes. They are not just extreme objects in isolation. They are key players in the story of how galaxies form, change, and sometimes stop forming new stars. There is also a quieter side to this dominance of gravity, one that has to do with time. Near a very massive object, the flow of time itself is affected. According to the theory of general relativity, gravity is not just a force pulling on objects, it is a curvature of space and time. The more mass you have, the more you bend this combined fabric. Close to a black hole, this bending becomes very strong. From the perspective of a distant observer, a clock near the event horizon would appear to run more and more slowly as it gets closer. In a sense, gravity not only wins over matter and light, but also over time. This does not mean that someone falling into a black hole would experience time slowing in a dramatic way from their own point of view. Their own clock would tick normally for them, but the outside universe would seem to speed up, racing through its future while they approach the boundary. This interplay between gravity and time adds another layer to the idea of winning. It is not just about pulling things inward. It is about reshaping the very stage on which events take place. As you listen, you might notice that this story, while rooted in physics, has a certain rhythm to it. A quiet beginning, a slow build, a tipping point, and then a new state, one that follows different rules than before. That pattern shows up in many places, not just in the formation of black holes, but in the formation of stars, the evolution of galaxies, and even in processes much closer to home. Water freezes, sand dunes form, societies grow and change. In each case, small interactions add up over time until something new emerges. In the case of the largest black holes, the emergence is particularly striking because it represents gravity operating at its most extreme. It is a place where the familiar concepts of solid objects, light and steady time give way to something more abstract, more challenging to picture. And yet, this extreme outcome is still rooted in the same simple rule we started with. Things with mass attract each other. That rule, applied over vast distances and long stretches of time, is enough to create stars, galaxies, and the largest black holes we have ever discovered. The universe does not need complicated instructions to build complex structures. It relies on a few basic principles, repeated and combined in countless ways. Most of the time, gravity is easy to overlook, but given enough room to work, it can shape the largest and most mysterious objects in the universe. If you trace any great structure in the universe far enough back, you eventually arrive at something small and unassuming. Mountains begin as slow shifts in rock, rivers start as narrow trickles. Even galaxies, with their sweeping arms and glowing cores, began as faint differences in the density of matter spread across a young, expanding cosmos. The same is true for the largest black holes. Before they became the heavy, quiet giants we talk about today, they started as something closer to a seed, a small beginning in a universe that was still learning how to arrange itself. The word seed is a helpful one here, because it suggests both fragility and potential. A seed on its own does not look like much. It is small, easy to overlook, and carries no obvious sign of the towering tree or sprawling plant it might one day become. But given the right conditions, time, and a steady supply of energy, it can grow into something far larger than its humble starting point would suggest. Black holes, in their own cosmic way, follow a similar path. To understand how a black hole can grow from something relatively modest into a giant that outweighs billions of stars, it helps to begin in the early universe, not long after everything we know came into existence. In those first hundreds of millions of years, the universe was a very different place. It was smaller, denser, and filled mostly with simple elements like hydrogen and helium. There were no heavy elements yet, no planets, no life, and no complex structures. But there were regions where matter was just a little bit more concentrated than average. Gravity began to work on those regions, pulling material inward, making them denser, and eventually forming the first stars. These early stars were not like the ones we see around us today. Many of them were enormous, far more massive than our Sun. Because they were so large, they burned through their nuclear fuel quickly. Their lives were short and intense, ending in dramatic collapses and explosions that scattered the first heavier elements into space. When some of these massive stars collapsed, they left behind black holes that were already larger than most stellar black holes we see forming in the universe now. These were among the first seeds. Another idea that scientists explore is that in some regions, instead of forming stars first, large clouds of gas might have collapsed directly into black holes. These so-called direct collapse black holes would have started their lives much larger than anything formed from a single star. If this process happened, it would give the universe a head start in building supermassive black holes. Whether the earlier seeds came from massive stars, direct collapse, or a combination of both, the important point is that they existed in a universe that was full of material and activity. Galaxies were forming and merging at a faster rate than they do today. Gas was more plentiful. The environment was rich with opportunities for growth. Once a black hole exists, its main way of gaining mass is through a process called accretion. This is the steady intake of matter from its surroundings. Gas clouds drifting through space can be drawn in by the black hole's gravity. As the gas falls inward, it does not usually plunge straight in. Instead, it begins to spiral, forming a rotating disk around the black hole. This disk, known as an accretion disk, becomes a place of extreme conditions. Friction between layers of gas causes it to heat up, sometimes to millions of degrees. At these temperatures, the gas glows, releasing vast amounts of energy in the form of light and other radiation. This is what makes quasars and active galactic nuclei so bright. The black hole itself remains dark, but the feeding process lights up the surrounding region like a cosmic beacon. Accretion is not always smooth and steady. It can happen in bursts depending on how much material is available and how it is distributed. A passing cloud of gas, the disruption of a star that wanders too close, or the merger of two galaxies can suddenly deliver a fresh supply of matter to the black hole's neighborhood. When that happens, the accretion rate can spike, and the black hole can grow more rapidly for a time. But there is a kind of natural limit to how fast a black hole can eat. As the accretion disk becomes brighter, the radiation it produces pushes outward on the incoming gas. If the outward pressure becomes strong enough, it can slow or even temporarily halt the inflow of matter. This balance between gravity pulling in and radiation pushing out sets a rough upper limit on the growth rate, known as the Eddington limit. This means that even under ideal conditions, a black hole cannot grow infinitely fast. It takes time, often hundreds of millions or billions of years, for a black hole to go from a seed to a giant. Time, in this context, is one of the most important ingredients. The universe is old, around 13.8 billion years. That may sound like an unimaginably long span, but when you're trying to build something that weighs tens of billions of times more than a star, every billion years counts. This is one reason why the discovery of extremely massive black holes in the early universe is so intriguing to scientists. If a black hole is already very large when the universe is only a few billion years old, it suggests that either it started from a very big seed, or it grew at an unusually high rate, or both. As black holes grow, they do not do so in isolation. They are embedded in galaxies, and those galaxies are part of larger structures like groups and clusters. The growth of a black hole and the growth of its host galaxy are closely linked. When a galaxy has a lot of cold gas, it can form new stars. That same gas can also feed the central black hole. As the black hole grows and becomes more active, the energy it releases can heat or push away some of that gas. This can slow down or even shut off star formation in the galaxy. This back and forth influence is sometimes described as a kind of conversation between the black hole and the galaxy. The galaxy provides the black hole with material to grow. The black hole, in turn, influences how the galaxy evolves. Over time, this interaction can lead to a balance where the size of the black hole and the properties of the galaxy are closely related. Observations show that in many galaxies, the mass of the central black hole is correlated with the mass of the galaxy's central bulge of stars. This suggests that their histories are intertwined, shaped by the same processes over cosmic time. Another important path to growth comes from mergers. Galaxies do not stay neatly separated forever. Gravity pulls them toward each other, especially in dense environments. When two galaxies collide, their stars mostly pass by one another without direct collisions, because the distances between stars are so large. But their gas clouds interact, compress, and form new stars. Their central black holes, after a long and complex dance, eventually come together. When two black holes merge, they form a single, more massive black hole. The process releases a tremendous amount of energy in the form of gravitational waves, which spread out through space. These waves carry information about the masses and spins of the black holes involved, and in recent years scientists have been able to detect them with instruments on Earth. Each merger is like adding another piece to a growing structure. Over billions of years, a black hole in the centre of a large galaxy might merge with many others, each time increasing its mass and extending its reach. This combination of steady accretion and occasional mergers is how black holes climb the ladder from small beginnings to enormous sizes. Now, consider what this looks like on the larger scales. In the biggest galaxies, often found at the centres of galaxy clusters, conditions are especially favourable for black hole growth. These galaxies sit in regions where matter is constantly flowing in, drawn by the combined gravity of hundreds or thousands of galaxies. Gas, stars, and even entire smaller galaxies can be funneled toward the centre. The central galaxy grows by absorbing its neighbours, its black hole grows by absorbing theirs. Over time, this can produce black holes with masses that stretch into the tens of billions of suns. These are the giants, the ones that push the limits of what we think is possible. As you listen to this, you might find it helpful to picture growth not as a smooth, straight line, but as a series of phases. There are quiet periods where the black hole grows slowly, sipping from a thin stream of gas. There are active periods where it blazes as a quasar, drawing in large amounts of material and lighting up its surroundings. And there are dramatic moments where mergers suddenly change the scale of everything. All of these phases are part of a long, complex history. There is also a sense in which black hole growth reflects the overall story of the universe itself. Early on, things happen quickly. structures form, merge and change at a rapid pace. As time goes on, the universe expands, matter becomes more spread out, and interactions become less frequent. Growth slows. The largest black holes we see today are, in many ways, fossils of a more active cosmic past. They carry the accumulated history of countless events, each one leaving its mark in the form of added mass and altered surroundings. This perspective can shift how we think about the word giant. It is tempting to imagine a largest black hole as something that was always destined to be huge, as if it were born special. In reality, it is more like the end result of a long chain of circumstances, opportunities and timing. A seed black hole that happens to form in a quiet, isolated galaxy with little gas may never grow very large. Another, forming in a dense, active region of the universe, may be swept up in mergers and streams of matter that allow it to grow far beyond the average. In that sense, the largest black holes are not just about mass. They are about location and history. They are records of where they formed and what they encountered along the way. As you follow this idea, you might notice how it echoes patterns closer to home. Growth often depends as much on environment as on inherent potential. The same seed planted in different soil, with different amounts of water and sunlight, can lead to very different outcomes. There is also a subtle connection to time here, not just in terms of duration, but in terms of sequence. For a black hole to become truly enormous, certain events need to happen in the right order. Gas needs to be available early. Mergers need to occur at times when the black hole can take advantage of them. The surrounding galaxy needs to remain massive enough to keep feeding the process. This layered, conditional growth makes the existence of the largest black holes feel almost like a kind of cosmic storytelling. Each one has a narrative, a unique path through the history of the universe, shaped by chance encounters and long-term trends. Now, let us return briefly to the object that often holds the title of the largest known black hole, the one associated with the distant quasar we mentioned earlier. The fact that it is so massive and that we see it at a time when the universe was relatively young suggests that its growth was both early and efficient. It likely formed in a region rich with material and underwent rapid accretion and possibly multiple mergers in its early history. Studying such objects helps scientists test their models of black hole formation and growth. If the models cannot produce something that massive in the time available, then the models need to be revised. In this way, the largest black holes act as benchmarks, pushing our understanding forward. As you listen, you might find yourself wondering what the ultimate limit is. Can black holes keep growing forever? Is there a maximum size they can reach? This is an open question. There are theoretical ideas about limits set by the availability of matter, the expansion of the universe, and the feedback between black holes and their surroundings. In a universe that continues to expand and become more diffuse, it may become harder for black holes to find enough material to keep growing at a significant rate. In the very distant future, growth may slow to a crawl. Black holes will still exist, but their era of rapid expansion may be long past. For now, though, in the present universe and the deep past we can still observe, growth is very much part of the story. The largest black holes are not sudden creations. They are the results of long, patient processes shaped by gravity, time, and the structure of the universe itself. What does it really mean to say one black hole is bigger than another? How do we draw the lines between large, very large, and the truly extreme? There is a point somewhere along the path of thinking about size where ordinary words start to feel a little thin. Big works well when you're talking about a tree, a building, or even a mountain. Bigger can stretch to cover oceans, continents, or perhaps a planet. But when you begin to talk about objects that outweigh billions of stars and influence regions of space larger than entire solar systems, those words begin to wobble. They still come out of our mouths, but they carry a kind of quiet admission that we are borrowing familiar language to describe something far beyond familiar experience. This is where the difference between big, bigger, And absolutely enormous becomes more than just a matter of numbers. It becomes a matter of perspective. Let us start in a place that feels comfortable. Think about the Sun. It is already an object of impressive scale. It holds more than 99% of the mass of our entire solar system. If you were to hollow it out and fill it with Earths, you could fit more than 1 million of them inside. Its gravity reaches out to keep distant icy objects in place far beyond the orbit of Pluto. In everyday terms, the Sun is enormous. Now imagine a black hole formed from a single massive star. These are often called stellar mass black holes. They usually weigh somewhere between a few times and a few tens of times the mass of the Sun. Compared to the Sun, that is bigger. Compared to a planet or a mountain, it is unimaginably larger, and yet in the grand hierarchy of black holes, it is still at the small end of the scale. Here is where the first shift in perspective happens. A stellar mass black hole can be heavier than our Sun, but its physical size, defined by its event horizon, can actually be quite small. A black hole with the mass of the Sun would have an event horizon only about 6 kilometers across. That is roughly the size of a small city. You could, in theory, drive across the diameter of such a black hole in less than an hour, if roads and gravity allowed such a strange journey. So already we see that big in terms of mass does not necessarily mean big in terms of physical width. Black holes compress a lot of mass into a very small region. Their size grows with mass, but not in the way we might intuitively expect. Now let us step up a level. Between stellar mass black holes and the supermassive ones that sit at the centres of galaxies, there is a middle category that scientists sometimes refer to as intermediate mass black holes. These are thought to weigh hundreds to hundreds of thousands of times the mass of the Sun. They are harder to find and study, partly because they are not as dramatic as quasars and not as common as stellar black holes. These intermediate black holes are like the quiet middle children of the black hole family. They're big enough to have a noticeable gravitational influence on their surroundings, but not so large that they dominate an entire galaxy. They might form in dense star clusters, where many stars interact and merge, or through the growth of smaller black holes over time. From here, the scale starts to climb quickly. Supermassive black holes are in a different category altogether. These are the ones that weigh millions or billions of times as much as the Sun. Our own galaxy, the Milky Way, has one at its centre. It is known as Sagittarius A star, and it weighs about 4 million suns. That is already a number that is difficult to hold in the mind. 4 million stars worth of mass, concentrated into a region smaller than the orbit of Mercury. Even at this level, we're still not near the top of the scale. In other galaxies, especially large, old ones, central black holes can reach masses of hundreds of millions or even several billion suns. These are the kinds of black holes that can power bright quasars, visible across vast stretches of the universe. And then, beyond even that, there are the truly extreme cases. These are sometimes called ultramassive black holes, a term that is not officially standardized, but used to describe black holes that push past the 10 billion solar mass mark. This is the territory of objects like the one associated with the quasar TON 618, which is estimated to weigh on the order of 60 billion suns. This is where absolutely enormous begins to feel like the only phrase that fits, even if it still falls short. To get a sense of what this means, let us try a different kind of comparison. Imagine lining up stars like grains of sand. Each grain represents a star the size of our Sun. A stellar mass black hole might be a small handful of those grains. A supermassive black hole like the one in our galaxy would be a small pile, perhaps enough to fill a cup. But an ultramassive black hole would be more like a truckload of sand, all poured into a single spot. Of course, even that image breaks down because sand and trucks are still things we encounter in everyday life. The reality is that we are dealing with a scale that does not map neatly onto human experience. Another way to think about it is in terms of influence. A stellar mass black hole mainly affects its immediate neighbourhood. It might orbit a companion star, pulling gas from it, or sit quietly in space, only noticeable if something wanders too close. a supermassive black hole affects the motion of stars in the central region of a galaxy. In our own Milky Way, astronomers can track the orbits of individual stars near the centre and see them moving at incredible speeds, all under the influence of Sagittarius A star. An ultramassive black hole, on the other hand, can shape the behaviour of an entire galaxy, and even its surroundings. The energy released by the material falling into it can heat gas on a galactic scale, influencing how and where new stars form. In some cases, powerful jets of particles are launched from the regions near the black hole, stretching far beyond the galaxy itself and into intergalactic space. So the difference between big, bigger, and absolutely enormous is not just a matter of adding more zeros to a number. It is a difference in role, in reach, and in the way these objects participate in the larger structure of the universe. There is also a subtle difference in how these black holes come to exist. Smaller black holes are closely tied to the lives and deaths of individual stars. Their story is local and personal, if you will, tied to a single system. The largest black holes, by contrast, have stories that are deeply entangled with the history of their entire galaxy and even the cosmic neighbourhood around it. Their growth reflects billions of years of mergers, gas flows, and large-scale structure formation. This brings us to another interesting distinction. When we talk about the size of a black hole, we often mean its mass. But mass is not the only way to think about size. The event horizon, the boundary beyond which nothing can escape, grows as the black hole becomes more massive. For a black hole the mass of the Sun, the event horizon is only a few kilometres across. For a black hole with 1 billion times the mass of the Sun, the event horizon would be about as wide as the orbit of Earth. For one with tens of billions of suns worth of mass, the event horizon can stretch out to distances comparable to the orbit of Neptune or beyond. This means that if you were somehow able to observe such a black hole from a safe distance, it would not look like a tiny dot. It would be a region of space, a sphere of darkness large enough to contain the entire inner solar system. And yet, even that immense sphere is small compared to the galaxy around it. This contrast is part of what makes the largest black holes so interesting. They are both dominant and relatively tiny at the same time. They are the heaviest single objects in their galaxies, but they still occupy only a small fraction of the total volume. Now let us turn to how astronomers draw the lines between these categories. There is no strict, universally agreed upon set of boundaries. The terms stellar mass, intermediate, supermassive, and ultramassive are useful labels, but they are more like signposts than hard rules. Part of the reason for this is that our observations are incomplete. We know a lot about stellar mass black holes in our own galaxy and nearby galaxies, because we can detect their effects on companion stars and nearby gas. We are learning more about supermassive black holes through observations of galactic centres and distant quasars. Intermediate mass black holes, however, remain elusive. They are harder to spot and harder to confirm. This means that the picture we have of the full range of black hole sizes is still being filled in. There may be more objects in the middle of the scale than we currently know about. There may even be black holes larger than the ones we have identified so far, waiting in regions of space we have not yet examined in detail. Another factor that complicates the idea of largest is uncertainty. When astronomers estimate the mass of a black hole, they rely on indirect measurements. They observe the motion of stars, the behaviour of gas, or the properties of light coming from the accretion disk. From these observations, they use models to infer how massive the black hole must be to produce those effects. These models are powerful, but they are not perfect. They come with ranges and error bars. This means that when we say a black hole weighs, for example, 60 billion suns, we really mean that it likely falls somewhere within a certain range around that number. This is why the title of largest black hole ever discovered is not a permanent crown. It can shift as new measurements refine old estimates, or as new objects are found. There is also an interesting philosophical angle to all of this. At some point, the difference between very large and absolutely enormous becomes more about human perception than about physical reality. To the universe, A black hole with 10 billion suns worth of mass and one with 60 billion suns worth of mass are both just outcomes of gravity and time. The labels we apply reflect our own attempt to organise and understand what we see. From a cosmic perspective, there is no special category for largest so far. There is just a continuous range of masses shaped by local conditions and history. And yet, we cannot help but be drawn to extremes. The tallest mountain, the deepest ocean trench, the brightest star, the largest black hole. These superlatives give us anchor points in a vast sea of information. They help us tell stories about the universe, to frame what we know in terms that feel meaningful. As you listen, you might notice that this tendency shows up in many areas of life. We mark the biggest moments, the longest journeys, the most important milestones. It is a way of creating structure, of finding highlights in an otherwise continuous flow. In the case of black holes, the highlight is not just about breaking a record. It is about what that record tells us. A black hole that massive, especially one seen in the early universe, challenges our understanding of how quickly and efficiently these objects can grow. It pushes scientists to refine their models of galaxy formation, cosmic structure, and the behaviour of matter under extreme conditions. So the difference between big, bigger, and absolutely enormous is also a difference in what questions get asked. A small black hole raises questions about the life of a star. A medium one raises questions about star clusters and galactic neighbourhoods. A truly enormous one raises questions about the history of the universe itself. There is another quiet layer to this, one that has to do with time. The largest black holes we see today are not just large in space, they are large in time. They carry with them the accumulated history of billions of years of cosmic activity. Each bit of mass they contain represents something that once existed as a star, a cloud of gas, or another black hole. In that sense, an ultramassive black hole is like a kind of archive. It is a single object that holds within it the results of countless past events, all compressed into one gravitational presence. This idea can shift how you think about size. It is not just about how much something weighs or how wide it is is about how much history it contains. Size in the universe is not just a number on a page. It is a story of growth, influence, and time, unfolding across distances and durations that quietly remind us how wide the cosmos really is. At some point in every long journey of understanding, there is a moment where the landscape changes. The familiar hills and paths give way to something broader, heavier, and more imposing, not in a threatening way, but in a way that makes you slow down and take in the view. This is where we find ourselves now, stepping into the realm of the Titans, the supermassive black holes that sit at the hearts of galaxies, shaping their surroundings not through noise or motion, but through presence alone. When people hear the word supermassive, it can sound like a dramatic flourish, a bit of scientific exaggeration, but in this case, the term is almost understated. These objects are not just large, they are in a class of their own, separated from smaller black holes by an enormous gap in mass, influence, and history. To begin understanding them, it helps to clear away one common image. Supermassive black holes are often imagined as roaming through space, hunting for stars and planets to pull in. In reality, they are more like anchors. They stay in one place, at the gravitational centre of their galaxy, while everything else moves around them. Stars orbit, gas clouds drift, entire spiral arms sweep past, all tracing paths shaped by the combined gravity of the galaxy and its central black hole. In our own Milky Way, this central black hole is known as Sagittarius A star. It is about 4 million times the mass of the Sun. That number alone is already enough to stretch the mind. And yet, as we have seen, this is on the smaller end of the supermassive range. Other galaxies host black holes that weigh hundreds of millions or billions of suns. These are the true heavyweights, the ones that can power quasars and light up the distant universe. So what exactly makes a black hole supermassive? The term refers primarily to mass. Stellar mass black holes, formed from collapsing stars typically range from a few to perhaps a few dozen times the mass of the Sun. Supermassive black holes start at around 1 million suns and go up from there. Between these two categories, there may be intermediate mass black holes, but the supermassive ones clearly stand apart. This leap in scale brings with it a leap in behaviour. A small black hole might spend most of its life quietly orbiting a companion star or drifting through space, only becoming noticeable when it pulls in a bit of gas or causes its partner star to behave in unusual ways. A supermassive black hole, by contrast, lives at the centre of a complex active environment. It is surrounded by dense fields of stars, swirling clouds of gas, and often a bright hot disk of material spiralling inward. One of the first things to notice about these giants is that, despite their name and reputation, they are not especially dense in the everyday sense. In fact, the larger a black hole becomes, the lower its average density can be. This might sound surprising. We often think of black holes as the ultimate in compression, matter packed into the smallest possible space, and at their cores, that idea still holds. But when you consider the size of the event horizon of a supermassive black hole, which can be as wide as the orbit of a planet or even larger, the mass is spread over a much bigger volume of space. If you were somehow able to drift across the event horizon of a supermassive black hole, you might not notice anything dramatic at the moment you crossed. The gravitational forces at that boundary can be quite gentle, compared to those near a smaller black hole, where tidal forces can be extreme. In that sense, the titans of the black hole world are strangely soft at their edges, even as they remain absolute in their grip. Of course, this is a purely theoretical thought. No one has ever come close to such a boundary, and even if they did, the journey beyond would not be something they could report back from. Now, let us consider where these supermassive black holes live. Nearly every large galaxy we have studied in detail appears to have one at its centre. Spiral galaxies like our own, elliptical galaxies that look like vast glowing clouds of stars, and even some smaller galaxies all show signs of a central black hole. This suggests that supermassive black holes are not rare accidents. They're a fundamental part of how galaxies form and evolve. This leads to a deep and still active area of research. Did galaxies form first and then grow black holes at their centres, or did early black holes help shape the formation of galaxies around them? The evidence suggests that the two processes are closely linked, growing together over cosmic time. One way scientists study this relationship is by looking at the motion of stars near galactic centres. In the Milky Way, astronomers have tracked the orbits of individual stars near Sagittarius A star for decades. These stars move at incredible speeds, tracing elongated paths that reveal the presence of a massive invisible object at the centre. By measuring how fast these stars move and how close they get to the centre, scientists can calculate the mass of the black hole. This method provides some of the most direct and reliable measurements of supermassive black hole masses, at least for galaxies close enough to observe in detail. For more distant galaxies, especially those hosting bright quasars, the approach is different. The intense light from the accretion disk can be analysed to determine how fast the gas is moving and how large the emitting region is. From this, astronomers infer the mass of the black hole. These techniques have revealed a striking pattern. The mass of the central black hole in a galaxy is often correlated with the mass of the galaxy's central bulge of stars. This suggests a shared history, a kind of co-evolution where the growth of the black hole and the growth of the galaxy influence each other. To understand how this influence works, it helps to look at what happens when a supermassive black hole becomes active. When there is plenty of gas near the centre of a galaxy, the black hole can begin to feed. As material spirals in, the accretion disk grows brighter and hotter. In some cases, powerful jets of particles are launched from the regions near the black hole's poles, shooting out at nearly the speed of light. These jets can extend far beyond the galaxy itself, interacting with the surrounding intergalactic medium. The energy they carry can heat gas, prevent it from cooling and forming new stars, or even push it out of the galaxy entirely. This means that a supermassive black hole can play a role in regulating star formation in its host galaxy. When it is very active, it can effectively shut down the galaxy's ability to form new stars, leading to a more passive, aging population of stars. When it is quiet, gas can cool and collapse, forming new generations of stars. This feedback process is one of the key reasons supermassive black holes are considered central players in galactic evolution. They are not just passive objects sitting at the centre, they are part of a dynamic system, influencing and being influenced by their surroundings. Now, let us shift our attention from behaviour to origin. As we touched on earlier, the question of how supermassive black holes form is still open. There are a few leading ideas, and they may all play a role in different environments. One possibility is that they grow from the remnants of the first massive stars. These early black holes would have been larger than most stellar black holes formed today, giving them a head start. Over time, through accretion and mergers, they could grow into the supermassive range. Another idea is that in the early universe, under the right conditions, large clouds of gas could collapse directly into black holes without forming stars first. These direct collapse black holes would start their lives already weighing thousands or even millions of suns, making it easier to reach supermassive sizes quickly. A third possibility involves dense star clusters, where many stars and smaller black holes interact. In such environments, repeated mergers could build up a larger black hole over time. The reality may be a combination of these processes, varying from one galaxy to another. What makes this especially interesting is the discovery of very massive black holes in the early universe. When we observe a quasar that is billions of light years away, we are seeing it as it was when the universe was only a fraction of its current age. If the black hole at its centre is already very large at that time, it challenges our understanding of how fast these objects can grow. This is where the titans become more than just impressive objects. They become tests of our theories. If our models of black hole growth cannot explain their existence, then something about those models needs to change. Now, consider for a moment what it means to meet one of these titans, even in a conceptual sense. You cannot see a supermassive black hole directly. You see the stars orbiting around it. You see the gas glowing as it heats up in the accretion disk. You see the jets and outflows interacting with their surroundings. The black hole itself remains hidden, defined by its influence rather than its appearance. This makes them a bit like characters in a story who never appear on stage, but whose actions shape everything that happens. You know they are there because of what you see happening around them. There is something quietly compelling about that. It suggests a different way of thinking about presence and impact. You do not always have to be visible to be central. As you listen, you might find your thoughts drifting to the idea of scale again. A supermassive black hole can outweigh millions or billions of stars, and yet those stars taken together still make up the vast majority of the galaxy's light, colour and texture. The black hole is dominant in terms of gravity, but the galaxy is dominant in terms of what we see. This contrast between invisible mass and visible structure is one of the recurring themes in modern astronomy. Dark matter, black holes, and other unseen components play crucial roles in shaping the universe, even though our eyes and telescopes often focus on the bright, glowing parts. In that sense, supermassive black holes fit into a broader pattern. They remind us that what we see is only part of the story. Now let us take a step back and think about the word Titan itself. In mythology, Titans are often ancient, powerful beings, part of the deep structure of the world. They are not usually the ones running around in everyday tales. They are the background forces, the ones that define the stage on which other stories unfold. There is a quiet parallel here. Supermassive black holes are ancient. Many of them formed early in the history of the universe. They have been present through the rise and fall of stars, the merging of galaxies, and the slow expansion of space itself. They are not active in every moment, but they are always there, shaping the long-term evolution of their surroundings. you might notice how the idea of meeting these titans does not really involve confrontation or drama. It involves observation, patience, and a willingness to infer rather than to see directly. Let the image of these quiet giants sit in your mind, vast in mass, central in influence, and mostly hidden from direct view. They are reminders that some of the most important things in the universe work behind the scenes, shaping the grand patterns we see without ever stepping into the light themselves. Far out beyond the familiar patterns of nearby stars and softly glowing galaxies, there is a place in the universe where light itself becomes a kind of messenger from another era. The photons that reach us from there have travelled for billions of years, crossing expanding space, slipping past clusters of galaxies, and finally landing in the mirrors of our telescopes on a small, quiet planet. It is through this long, patient journey of light that we first became aware of an object so massive, so quietly dominant, that it reshaped how scientists think about the upper limits of what a black hole can become. This is where we meet the one that changed everything, not because it broke a record in a dramatic headline-grabbing way, but because it challenged the comfortable boundaries of our understanding. It sits at the heart of a distant quasar known by a simple, almost modest name, TON 618. The name does not hint at the scale of what it represents, but the object behind it does. To ease into this, let us take a moment to consider what a quasar actually is, because the largest known black hole does not reveal itself directly. It announces its presence through a brilliant energetic display that can outshine entire galaxies. A quasar forms when a supermassive black hole is actively feeding. Gas and dust fall toward it, swirling into a wide, flat disk. Friction, compression, and intense gravitational forces heat this disk to extraordinary temperatures. The material glows across the electromagnetic spectrum, from radio waves to visible light to X-rays. In some cases, jets of particles are launched from the region near the black hole's poles, shooting outward at nearly the speed of light. From across the universe, all of this activity blends into a single, extremely bright point of light. To an observer, a quasar can look like a star, even though it is actually the luminous heart of a distant galaxy. TON 618 is one of these points of light, but when astronomers studied it more closely, they realized that something about it was different. The brightness, the motion of the gas around it, and the properties of its light all pointed to a black hole of extraordinary mass. Estimates suggest that the black hole at the center of TON 618 weighs on the order of 60 billion times as much as our Sun. That number is not just large. It sits in a range that few other known black holes approach. To get a sense of what this means, it can help to return briefly to something more familiar. Our Sun is massive enough to dominate the entire solar system. Its gravity holds planets, asteroids, and distant icy bodies in place over a region that spans many billions of kilometers. Multiply that mass by 60 billion, and you begin to approach the gravitational presence of the black hole in TON 618. If you could place this black hole where the Sun is now, its event horizon, the boundary beyond which nothing can escape would extend far beyond the orbit of Neptune. The inner solar system, the outer solar system, and everything in between would all fit comfortably inside the region of space defined by its gravitational edge. And yet, even at that scale, the black hole would still be a small part of the galaxy it lives in. This contrast between immense local dominance and relative smallness in a larger structure is one of the quiet themes that runs through the study of the universe. Now, let us shift from what this object is to where it is. TON 618 lies more than 10 billion light-years away from Earth. That distance is not just a measure of space, it is also a measure of time. The light we see from it today left its surroundings when the universe was much younger than it is now. Our planet did not yet exist. The Sun had not yet formed. The Milky Way itself was still taking shape. This means that when we observe TON 618, we are not seeing it as it is in the present moment. we are seeing a snapshot of what it was in the distant past. This adds another layer of significance to its size. A black hole that massive, existing at such an early stage in the universe, raises important questions. How did it grow so quickly? What conditions allowed it to gather so much mass in a relatively short cosmic time? These questions are part of what makes TON 618 a turning point in the study of black holes. It does not just sit at the top of a list, it pushes against the edges of our models and forces scientists to consider new possibilities. To understand how astronomers arrived at their estimate of its mass, it helps to look at the methods they use. With nearby black holes, scientists can track the motion of individual stars orbiting close to the centre of a galaxy. By measuring how fast these stars move and how their paths curve, they can calculate the mass of the invisible object they are orbiting. For something as distant as TON 618, individual stars are far too faint and crowded to observe in this way. Instead, astronomers rely on the light from the quasar itself. The glowing accretion disk around the black hole produces light that can be spread out into a spectrum. This spectrum contains information about the speed and composition of the gas in the disk. Certain features in the spectrum, known as emission lines, broaden when the gas is moving quickly. By measuring how wide these lines are and how bright the quasar is, scientists can estimate the size of the region, emitting the light and the speed of the gas. From this, they infer how strong the gravitational pull must be, and therefore how massive the black hole is. These measurements come with uncertainties. They are not like weighing an object on a scale. They involve models, assumptions, and ranges of possible values. Even so, multiple studies using different approaches have arrived at similarly extreme estimates for TON 618. What stands out is not just the raw number, but how far it sits from the typical range. Most supermassive black holes weigh millions or billions of suns. TON 618 appears to be in a category of its own, or at least at the very top end of a rare group. This has led some researchers to refer to such objects as ultra-massive black holes, a way of signalling that they go beyond the usual definition of supermassive. Now let us take a moment to consider what it means for something like this to exist at all. In the early universe, matter was more densely packed. Galaxies were closer together. Mergers were more frequent. Gas was more abundant. All of these factors can contribute to rapid black hole growth. But even in that environment, building something as massive as the black hole in TON 618 is not straightforward. There are limits to how fast a black hole can grow through accretion, set by the balance between gravity pulling material in and radiation pushing it away. This suggests that either TON 618 started from a very large seed, or it found itself in an exceptionally favourable environment, or both. One idea is that it may have formed in a region where multiple galaxies merged early on, funneling large amounts of gas and smaller black holes into a central location. Another possibility is that it began as a direct collapse black hole, forming from the collapse of a massive gas cloud rather than from a single star. These scenarios are still being explored, and TON 618 serves as a kind of testing ground for them. If scientists can understand how this black hole grew, they can apply that understanding to other objects and build a more complete picture of black hole formation in general. There is also a broader implication here, one that extends beyond black holes themselves. If objects like TON 618 were common in the early universe, they would have had a significant impact on the formation of galaxies. The energy released by their accretion disks and jets could have heated surrounding gas, influencing where and when stars could form. This means that the largest black holes may have played a role in shaping the large-scale structure of the universe, not just as passive gravitational centres, but as active sources of energy and feedback. As you sit with this idea, you might notice how it changes the way you think about the phrase, the one that changed everything. It is not just about changing our scientific theories. It is also about how such an object might have changed its own cosmic neighbourhood. Now, let us return to the experience of discovery. TON 618 was not found in a single moment of realization. It emerged gradually through surveys of the sky, catalogues of quasars and careful follow-up observations. As astronomers measured its properties and compared them to others, its exceptional nature became clear. This process reflects a broader pattern in science. Big discoveries often come not from a single, dramatic observation, but from the accumulation of many small, careful steps. Data is collected, analysed, questioned, and refined. Patterns emerge slowly. There is something quietly fitting about this when it comes to black holes. Objects that are defined by patience, gravity, and long time scales are revealed through equally patient and methodical work. It is also worth noting that TON 618 holds its title only for now. Science does not deal in permanent records. It deals in current best estimates. There may be black holes out there that are just as massive, or even more so, hidden in regions of space we have not yet studied in detail. As telescopes become more powerful and surveys become more comprehensive, new candidates may emerge. This does not diminish the significance of TON 618. Instead, it places it within an ongoing story, one where each discovery opens the door to the next. Now, let us pause for a moment and consider what it means, on a human level, to talk about something like this. We are discussing an object that is billions of light years away, that outweighs billions of stars, and that exists on timescales that make human history look like a brief flicker. And yet, here we are, on a planet orbiting a fairly ordinary star, able to detect its presence and estimate its mass. This connection across such vast distances and times is one of the quiet marvels of science. The same physical laws that govern the motion of your hand or the flow of air in a room also govern the behaviour of gas around a black hole at the edge of the observable universe. When you think about it this way, TON 618 is not just a distant, abstract object. It is part of the same system of reality that includes you, your surroundings, and every small, everyday event. There is also a subtle shift in perspective that can come from contemplating something so extreme. It can make everyday concerns feel lighter, if only for a moment. It can remind you that the universe is wide, deep, and full of things that exist far beyond the immediate scope of daily life. This is not to say that the details of everyday life are unimportant. It is simply to say that there is room, sometimes, to let the mind wander outward and take in a larger view. As this part of our exploration continues, it is worth keeping in mind that TON 618 is both a specific object and a symbol. It is specific in the sense that it has a location, a mass, a spectrum of light, and a measurable history. It is a real, physical thing that can be studied and compared to others. It is also symbolic in the sense that it represents the extreme end of a process that happens throughout the universe. Black holes grow everywhere, in many galaxies under many conditions. TON 618 simply happens to sit at the far end of that range, making it a useful marker for what is possible. Now, let us gently turn our attention to how this object fits into a broader family. There are other very large black holes that compete for the title of largest. Some sit in the centres of massive galaxies in the nearby universe. Others power distant quasars similar to TON 618. Each of these objects has its own story, its own environment, and its own path of growth. Comparing them helps scientists identify common patterns and important differences. This is where the idea of meeting the largest known black hole becomes more than just focusing on a single object. It becomes a way of exploring a whole class of extreme phenomena. For now, let the image of TON 618 rest in your mind as a kind of quiet landmark, a point in the vast map of the universe that marks an edge, not a physical edge, but an edge of knowledge. It stands as a reminder that the universe is capable of building things far beyond what we can easily imagine, and that our role, as observers and thinkers, is to keep tracing the outlines of those things, slowly and carefully, as far as our tools and curiosity will allow. Across the vast stretches of space there are countless things that shine, shimmer, and announce themselves with light. Stars glow steadily. Galaxies spill their combined radiance into wide, hazy smears across the sky. Even clouds of gas can light up when they are energized by nearby activity. But black holes do none of these things. They sit in the middle of all this brightness as quiet absences, defined not by what they show, but by what they take away. And yet, despite this invisibility, we speak about their masses, their sizes, and their influence with surprising confidence. That confidence does not come from seeing them. It comes from learning how to read the subtle signatures they leave behind. To begin understanding how scientists measure something that cannot be seen, it helps to think of the universe as a kind of stage. Even when a main character never steps into the spotlight, the movement of the other actors can still reveal where they are standing. A black hole in this sense is a presence felt through motion, light, and distortion. It announces itself through effects rather than appearance. Let us start with one of the simplest and most direct clues: movement. In everyday life, you can often tell that something heavy is nearby without seeing it. If you roll a ball across the floor and it suddenly curves to one side, you might suspect there is a slope, or a heavy object pulling it. In space, stars and clouds of gas play the role of those rolling balls. They move along paths shaped by gravity, and by watching those paths carefully, astronomers can infer what is doing the pulling. In galaxies close enough to study in detail, this method can be remarkably precise. Near the centre of the Milky Way, for example, astronomers have spent decades tracking individual stars as they loop around an invisible point. Some of these stars complete their orbits in just a few years, moving at thousands of kilometers per second. The only thing that can keep them moving that fast without flying away is an object with a tremendous amount of mass concentrated into a very small region. By mapping these orbits, measuring their speeds, and applying the laws of gravity, scientists can calculate how massive that central object must be. This is how the mass of our own galaxy's black hole has been determined with high accuracy. This approach, however, relies on being close enough to see individual stars. For black holes in distant galaxies, and especially for those in faraway quasars, this level of detail is impossible. The stars blur together into a single glow. The centre of the galaxy becomes a bright point rather than a field of distinct objects. So astronomers turn to another kind of clue: light itself. Even though a black hole does not emit light, the material around it often does, and it does so in dramatic ways. Gas falling toward a black hole forms an accretion disk, and as this disk heats up, it produces light across a wide range of wavelengths. This light carries information about the motion, temperature, and composition of the gas that produced it. One of the most useful tools for extracting that information is a technique called spectroscopy. This involves spreading light out into its component colours, much like a prism turns white light into a rainbow. When you look at this rainbow in detail, you can see dark lines or bright lines at specific wavelengths. These lines correspond to the presence of particular elements and the conditions under which the light was emitted. Now, here is where motion comes back into the story. If a source of light is moving toward you, its light is shifted slightly toward the blue end of the spectrum. If it is moving away, the light shifts toward the red end. This is known as the Doppler effect, and it works for sound as well as light. It is why the pitch of a passing siren changes as it moves past you. In the accretion disk around a black hole, gas is moving at very high speeds. Some of it is moving toward us, some away from us, and some in directions in between. This causes the spectral lines in the light to spread out, or broaden. The faster the gas is moving, the broader these lines become. By measuring how wide these lines are, astronomers can estimate how fast the gas is moving, and from that they can infer how strong the gravitational pull must be to keep it in orbit. A stronger pull means a more massive black hole. This method is especially useful for studying quasars, where the light from the accretion disk is bright enough to be seen across billions of light years. Even though the black hole itself remains invisible, the behaviour of the gas around it provides a kind of indirect window into its mass. There is another layer to this technique that adds even more information. The brightness of the quasar can be used to estimate the size of the region producing the light. Brighter objects generally involve larger or more energetic emitting regions. By combining estimates of the region's size with measurements of the gas's speed, astronomers can calculate the mass of the central black hole. These calculations are not simple, and they rely on models of how accretion disks behave. Scientists test these models by comparing them to observations of closer, better understood systems. Over time, the models are refined and the estimates become more reliable. Now, let us step back and consider another kind of clue: bending. According to the theory of general relativity, mass bends the fabric of space and time. This means that light passing near a massive object will follow a curved path. This effect, known as gravitational lensing, can make distant objects appear distorted, magnified, or even multiplied. In some cases, a black hole or a galaxy containing a black hole can act as a lens for light from something even farther away. By studying how the background light is bent, astronomers can learn about the mass of the object doing the bending. This method is often used to study the mass of entire galaxies or clusters of galaxies, but it can also provide information about the distribution of mass near their centres. While it is not usually the primary way black hole masses are measured, it adds another piece to the overall picture. There is also a more subtle approach that involves timing. In some systems, especially those involving smaller black holes and companion stars, astronomers can observe regular changes in brightness or other properties as objects orbit each other. By measuring the period of these changes, they can determine the size of the orbit and the masses involved. For supermassive black holes, a related idea comes into play in the study of something called reverberation mapping. This technique looks at how changes in the brightness of the accretion disk are echoed in the surrounding gas clouds. When the disk brightens, the light takes a certain amount of time to reach these clouds and make them glow. By measuring this delay, astronomers can estimate the distance between the disk and the clouds. Combined with measurements of gas speeds, this can lead to another estimate of the black hole's mass. All of these methods share a common theme. They do not involve looking at the black hole directly. They involve looking at how it influences its surroundings. In a way, this makes black hole measurement a kind of cosmic archaeology. Scientists are not uncovering a visible object. They're reconstructing something hidden from the traces it leaves behind. Now, let us consider what this means in practice for something as distant and extreme as the black hole in a quasar like TON 618. The light from such an object has travelled for billions of years before reaching Earth. Along the way, it has passed through intergalactic space, through clouds of gas and past other galaxies. Each of these encounters can slightly alter the light, adding noise or distortion to the signal. When that light finally reaches a telescope, it is collected by mirrors or antennas and converted into data. That data is then processed, calibrated, and analysed. Background signals are subtracted. Instrumental effects are corrected. What remains is a carefully cleaned spectrum or image that scientists can study. From there, the work becomes a blend of observation and theory. The observed properties of the light are compared to models of how accretion disks and gas clouds behave around black holes of different masses. The mass that best matches the data is chosen as the most likely value, often with a range of uncertainty. This process is repeated by different teams using different instruments and methods. When multiple approaches converge on similar results, confidence grows. It is worth pausing here to reflect on how indirect this all is. We are not measuring a solid object that reflects light or casts a shadow in a straightforward way. We are measuring the motion of gas, the bending of light, and the timing of echoes, all at distances that make even the nearest star seem close by comparison. And yet, through this layered approach, scientists can estimate the mass of an invisible object billions of light years away to within a factor of a few. That is a remarkable achievement, even if it comes with caveats and uncertainties. There is also a human element to this process that often goes unmentioned. Behind every measurement is a group of people who designed the instruments, planned the observations, wrote the software, and debated the interpretations. Data is checked and rechecked. Results are compared with previous studies. Papers are reviewed and critiqued by other scientists. This slow, careful process is part of what gives the final numbers their weight. They are not just the output of a single calculation. They are the product of a community working over years or decades to refine its understanding. Now let us turn to another kind of measurement that has emerged more recently, one that does not rely on light at all. Gravitational waves, the ripples in space caused by accelerating masses, offer a new way to study black holes. When two black holes merge, they release a burst of these waves that can be detected by sensitive instruments on Earth. From the shape and timing of these signals, scientists can determine the masses and spins of the black holes involved in the merger. So far, this method has been most effective for studying smaller black holes and neutron stars, because the mergers of supermassive black holes produce waves with frequencies that are difficult to detect with current technology. In the future, space-based detectors may be able to observe these low-frequency waves, opening a new window on the growth and interaction of the largest black holes in the universe. This adds another layer to the idea of measurement. We're not limited to light. We are beginning to use the fabric of space itself as a kind of sensor. As you listen, you might notice how this whole process reflects a broader pattern in science. When something cannot be observed directly, scientists look for indirect evidence. They build chains of reasoning that connect what they can measure to what they want to know. This approach is not unique to astronomy. It shows up in many fields, from studying the interior of the Earth through seismic waves, to understanding the behavior of subatomic particles through their decay products. In each case, the challenge is the same. How do you learn about something you cannot see, touch, or interact with directly? The answer is to pay close attention to how it affects everything else. There is a quiet elegance in that strategy. It suggests that nothing in the universe exists in complete isolation. Even the darkest, most hidden objects leave some kind of mark on their surroundings. Now let us bring this back to the experience of listening and thinking about these ideas. It can be tempting to focus on the technical details, the instruments, the equations, the models. Those are important, but there is also a more general lesson here. Understanding often comes not from staring harder at the thing you want to know, but from widening your view and looking at the context around it. In the case of black holes, the context is everything. Stars, gas, light, space, time, and even the subtle ripples of gravity itself all become part of the story. The universe is full of things that cannot be seen directly, but that can still be known through patience, observation, and careful reasoning. Even in the deepest darkness, there are always traces, always signs, always subtle clues waiting to be noticed. The story of the largest black holes is not written in light alone. It is written in motion, in distortion, in echoes, and in the quiet, persistent patterns that reveal themselves when someone takes the time to look closely enough. Around a single invisible center, an entire city of stars can slowly take shape. Not in streets and towers, but in vast, spiraling arms and glowing clouds that stretch across tens or even hundreds of thousands of light years. This is the quiet architecture of a galaxy, and at the heart of many of them sits a presence that cannot be seen directly, yet influences everything around it. The idea that a galaxy can be built, in part, around a region of darkness may sound like a contradiction at first, but in the universe it is a surprisingly common arrangement. To ease into this, it helps to picture a galaxy not as a flat image in a book or on a screen, but as a three-dimensional structure. Stars are not arranged in a single plane. They form a thick disk, a central bulge, and a surrounding halo that extends far beyond what the eye can easily trace. Gas and dust weave through these regions, sometimes clumping into bright nurseries of new stars, sometimes drifting quietly in long, faint streams. All of this is held together by gravity, the shared pull of every bit of mass within the system. At the very center of this structure, in most large galaxies, there is a supermassive black hole. It does not shine. It does not mark its location with a visible beacon. And yet, its gravitational influence helps define the shape and behaviour of the entire system. Now, it is important to be clear about one thing. The black hole at the centre of a galaxy is not the sole force holding that galaxy together. The combined mass of billions of stars, along with large amounts of dark matter, plays a much larger role in shaping the overall structure. The black hole's direct gravitational reach is strongest in the central region, where stars move at incredible speeds and gas swirls in tight orbits. Even so, the presence of a supermassive black hole at the heart of a galaxy seems to be more than a coincidence. Observations suggest that the properties of the black hole and the properties of the galaxy are linked in subtle and important ways. One of the most striking patterns astronomers have found is a relationship between the mass of a galaxy's central black hole and the mass of the galaxy's central bulge of stars. This bulge is the dense rounded region in the middle of many galaxies, especially spiral ones like the Milky Way. The bigger the bulge, the more massive the black hole tends to be. This connection hints at a shared history. It suggests that as galaxies grow and evolve, their central black holes grow alongside them, each influencing the other over long periods of time. To understand how this influence works, it helps to think about the flow of material within a galaxy. Galaxies are not static. Gas moves through them, driven by gravity, by the pressure of radiation from stars, and by the energy released in events like supernova explosions. This gas can cool, collapse, and form new stars. It can also drift inward toward the centre. When enough gas reaches the central region, it can begin to feed the supermassive black hole. As this happens, the black hole becomes active, and the accretion disk around it can grow bright and energetic. This is when a galaxy's centre can transform into something like a quasar or an active galactic nucleus. The energy released during these active phases does not stay neatly confined to the immediate surroundings. It can travel outward in the form of radiation and high-speed jets of particles. These outflows can interact with the gas in the galaxy, heating it, pushing it away, or preventing it from cooling and forming new stars. In this way, the black hole can influence the future of the galaxy. If it becomes very active, it can slow down or even shut off star formation in the central regions. Over time, this can change the overall appearance and behaviour of the galaxy. This process is often referred to as feedback, and it is a key part of modern models of galaxy evolution. The idea is that galaxies and their central black holes are locked in a long-term interaction. The galaxy provides the black hole with material to grow. The black hole in turn regulates how the galaxy uses its gas. This balance does not always stay the same. There can be periods of relative calm, where the black hole is quiet and star formation proceeds steadily. There can also be periods of intense activity, where the black hole's influence becomes more dramatic. Now let us take a closer look at the different parts of a galaxy and how they relate to this central darkness. The innermost region is the core, where stars are packed more densely than in the outer areas. Here, the gravitational influence of the black hole is strongest. Stars move in complex, often elongated orbits, some passing very close to the centre before swinging back out again. These motions provide some of the clearest evidence for the presence and mass of the black hole. Surrounding the core, there is often a bulge of older stars. This region is more rounded and less structured than the spiral arms of a disk galaxy. The stars here tend to be older and redder, indicating that much of the star formation happened long ago. Beyond the bulge, in spiral galaxies, there is the disk. This is where the familiar spiral arms appear, marked by bright young stars and clouds of gas and dust. This region is often more active in terms of ongoing star formation. Even farther out, there is a halo of stars and dark matter that extends well beyond the visible edges of the galaxy. This halo plays a major role in the galaxy's overall gravitational field, even though it is faint and difficult to observe directly. The supermassive black hole sits at the centre of all of this, embedded within the core. Its influence is most obvious there. but through feedback processes and long-term interactions, it can affect the galaxy on much larger scales. Now, consider what this means for a galaxy that hosts one of the largest black holes known. In such a system, the central black hole can be so massive that its active phases release enormous amounts of energy. This energy can shape the surrounding gas on a galactic scale, creating large cavities, shock fronts, and streams of hot plasma. Observations of some massive galaxies show giant bubbles of hot gas extending far from their centres, likely inflated by past activity from their central black holes. These structures can be hundreds of thousands of light years across, large enough to encompass multiple smaller galaxies. This suggests that in the most extreme cases, the black hole's influence is not just a local effect. It becomes a defining feature of the galaxy's environment. There is also a connection between the size of the black hole and the type of galaxy it lives in. The largest black holes tend to be found in the most massive galaxies, often giant elliptical galaxies that sit at the centres of galaxy clusters. These galaxies are usually old and have relatively little ongoing star formation. Their stars are mostly ancient, and their structure is smooth and rounded rather than spiral. These central galaxies have often grown through many mergers with smaller galaxies. Each merger adds stars, gas, and potentially another black hole to the system. Over time, this process can build both a massive galaxy and a massive central black hole. In contrast, smaller, more isolated galaxies often host smaller black holes. Their growth histories are different, shaped more by steady star formation and less by dramatic mergers. This pattern reinforces the idea that the largest black holes are products of particularly active and crowded cosmic environments. Now, let us take a moment to think about what a galaxy built around such a central darkness might look like from the inside. Imagine being in a star system near the centre of a massive galaxy. The night sky would be filled with stars, far more densely packed than what we see from Earth. The central region would glow with the combined light of millions of suns. If the black hole were in an active phase, there might be a bright, energetic source at the very centre, outshining everything else in the sky. The radiation and high-energy particles could affect the surrounding space, altering the conditions for star formation and potentially influencing the environments of nearby star systems. On the other hand, if the black hole were quiet, the galaxy might appear relatively calm, with star formation proceeding in the outer regions and older stars dominating the inner bulge. This variability over time is another important aspect of the relationship between galaxies and their central black holes. They do not exist in a single fixed state. They evolve together, passing through different phases over billions of years. There's also a more subtle, long-term effect to consider. As the universe expands and galaxies move farther apart, the rate of mergers slows down. Gas becomes more spread out. The opportunities for rapid growth, both for galaxies and for black holes, become less frequent. In the distant future, many of the largest galaxies will have used up or lost much of their gas. Their black holes will become quieter, fed only by the occasional wandering star or cloud of dust. At that point, the relationship between the galaxy and its central black hole will shift again. The black hole will remain as a massive dark presence, but its role as an active regulator of star formation will fade. This long-term perspective adds another layer to the idea of a galaxy built around a central darkness. It is not just about structure in space. It is also about structure in time. The galaxy and the black hole grow together, influence each other, and eventually settle into a more stable, quieter state. Now, let us bring this back to the specific case of a galaxy hosting one of the largest black holes known, like the one associated with the distant quasar we have been discussing. In that system, the black hole's immense mass suggests a long and active history. The galaxy around it likely experienced many mergers and periods of intense gas inflow. Its central region may have gone through phases of extreme brightness, visible across much of the observable universe. Over time, as the black hole released energy and shaped its surroundings, the galaxy's structure would have been influenced in subtle and not so subtle ways. Star formation may have been redirected, gas reservoirs heated or dispersed, and the overall balance of the system adjusted. Studying such systems gives astronomers a window into these processes. By comparing galaxies with very large black holes to those with smaller ones, they can look for patterns in star formation rates, gas content, and overall structure. These comparisons help refine our understanding of how galaxies evolve over cosmic time and how central black holes fit into that story. There is also a quiet philosophical dimension to all of this. A galaxy is a collection of hundreds of billions of stars, each one potentially hosting its own planets, and, perhaps, its own histories. At the centre of this vast community, there is a region of space that cannot be seen, that does not shine, and that will never send out a direct signal of what lies within it. And yet, that region plays a central role in the life of the entire system. This can invite a different way of thinking about importance and influence. In human terms, we often associate importance with visibility, with being seen and recognized. In the universe, some of the most influential things are the ones we cannot see directly at all. Now let us turn our attention to how astronomers actually map these galactic structures and study the relationship between the visible parts and the invisible center. Telescopes operating at different wavelengths reveal different aspects of a galaxy. Optical telescopes show the light from stars. Radio telescopes can trace cold gas. X-ray telescopes can detect hot, energetic regions near the black hole. By combining these views, scientists can build a multi-layered picture of how matter is distributed and how energy flows through the system. This layered approach is especially important for studying galaxies with active central black holes, where processes at the core can have effects far beyond the immediate vicinity. As you listen, you might notice how this mirrors the earlier discussion about measuring black holes. In both cases, understanding comes from looking at patterns and relationships rather than direct observation. We cannot see the black hole, we cannot see gravity itself, but we can see what they do. This theme of learning about the unseen through the seen runs through much of astronomy and, in a broader sense, through much of human knowledge. Stars are born and die, gas flows and cools, black holes grow and quiet down. Over billions of years, the system reshapes itself again and again. At the centre of it all, there remains that region of darkness, not as an absence, but as a presence, a constant participant in the long story of the galaxy. Beneath the steady ticking of clocks and the familiar rhythm of days and nights, there is a deeper layer to time that most of us rarely have reason to think about. We tend to treat it as a simple backdrop, something that flows the same way for everyone, everywhere, like a quiet river carrying all events along at a constant pace. But when you move far from the ordinary environments of planets and stars and begin to approach something as massive as a supermassive black hole, that comfortable idea starts to loosen. Time, it turns out, is not as rigid or uniform as it feels in everyday life. Near something this heavy, it behaves in ways that challenge intuition and invite a slower, more careful kind of attention. To begin easing into this, it helps to shift how you think about gravity itself. In classical physics, gravity is often described as a force, something that pulls objects toward each other. You drop a stone, and it falls. The Earth pulls it down. That picture works well for most practical purposes, but it is not the full story. According to the theory of general relativity, gravity is better understood as a bending of space and time. Mass and energy tell space-time how to curve, and that curved space-time tells objects how to move. In this view, a planet does not orbit a star because it is being pulled by an invisible rope. It follows the curved path laid out by the shape of space and time around the star. This idea might sound abstract, but it leads to very real and measurable effects. One of those effects is that time itself runs at different rates in different gravitational environments. Here on Earth, the difference is subtle. A clock at sea level, closer to the planet's centre of mass, ticks slightly more slowly than a clock on a mountaintop. The difference is tiny, far too small to notice in daily life, but sensitive instruments can measure it. This is not a quirk of technology. It is a fundamental feature of how time works in a gravitational field. Now imagine taking that same principle and applying it not to a planet, but to a black hole that weighs billions of times more than the Sun. As you move closer to such an object, the curvature of space-time becomes more extreme. The paths that light and matter can follow become more tightly constrained, and the rate at which time passes, relative to a distant observer, slows down more and more. From the perspective of someone far away, watching from a safe distance, a clock carried by an object falling toward a black hole would appear to tick more slowly as it gets closer. The closer it gets to the event horizon, the boundary beyond which nothing can escape, the slower that clock seems to run. The light coming from the falling object becomes more and more stretched, shifting toward the red end of the spectrum, fading and dimming. In this distant observer's view, the object never quite crosses the event horizon. It appears to slow down and freeze, hovering at the edge, growing fainter until it effectively disappears from sight. This picture has become one of the most well-known illustrations of how time behaves near a black hole. It is often described as time stopping at the event horizon. But this is only half of the story, and it depends on who you ask. From the perspective of the object itself, or of someone travelling along with it, time does not stop. Their own clock ticks normally. Their heartbeat, their thoughts, their internal sense of duration all proceed as usual. They cross the event horizon without noticing a sudden pause or a dramatic moment. The difference lies not in their experience, but in how that experience is seen from the outside. This difference in perspectives highlights something important. Time is not just a single, universal flow that everyone shares. It is local. It depends on where you are and how you're moving. Near a supermassive black hole, this localization of time becomes especially pronounced. Let us take a moment to imagine a scenario, not as a dramatic plunge, but as a gentle approach. Picture a spacecraft equipped with a very precise clock, slowly drifting toward a supermassive black hole from a great distance. Far away, another observer, also with a precise clock, watches this approach. At first, the two clocks stay in close agreement. The difference in gravitational field is small, and time passes at nearly the same rate for both. As the spacecraft gets closer, the difference begins to grow. The clock on the spacecraft starts to lag behind the one far away, not by minutes or seconds at first, but by fractions of a second, then seconds, then more. The closer it gets, the greater the difference becomes. If the spacecraft could hover just outside the event horizon, its clock would appear to run extremely slowly compared to the distant one. A few seconds for the crew might correspond to hours, days, or even years for the observer far away, depending on how close the spacecraft is to that boundary. This effect is known as gravitational time dilation, and it is one of the most striking predictions of general relativity. Now, when we talk about something as massive as the black hole associated with a distant quasar, this effect becomes especially dramatic. The event horizon of such a black hole can be as large as the orbit of a planet or more. That means there is a wide region of space where gravitational time dilation is significant, not just a tiny zone near a point-like centre. This leads to a fascinating possibility. There could be regions around a supermassive black hole where time for an object moving along a certain path passes much more slowly than it does for the rest of the galaxy. In practice, this does not mean that stars or planets are experiencing wildly different timelines in any simple, isolated way. The motions of stars near a galactic centre are complex, and they do not sit still near the event horizon. They orbit at varying distances, passing through regions of stronger and weaker gravitational influence. Still, the principle remains. The deeper you go into a gravitational well, the more time is affected. This connection between gravity and time also has consequences for how black holes grow and how they interact with their surroundings. Material falling toward a black hole experiences increasing gravitational time dilation. From the point of view of the distant universe, processes near the black hole appear to slow down. This affects how we interpret the light and radiation coming from the accretion disk and nearby regions. It means that when we observe a quasar, we are seeing events that are, in a sense, stretched out in time compared to how they are experienced locally. There is also another layer to this story, one that involves motion as well as gravity. Special relativity tells us that time also slows down for objects that are moving very fast. Near a black hole, both effects can come into play at the same time. Gas in the accretion disk can be moving at a significant fraction of the speed of light, while also sitting deep in a gravitational field. This combination leads to complex patterns in the light we observe. The light can be shifted in frequency, brightened in some directions and dimmed in others, all because of the interplay between motion, gravity, and the curved paths that light follows. Astronomers use these patterns to learn about the environment near the black hole. By carefully analysing how the light is distorted, they can infer how fast the gas is moving and how strong the gravitational field is. In this way, time dilation itself becomes a kind of tool for studying black holes. Now, let us step back and think about what this means on a more conceptual level. In everyday life, we often think of time as something separate from space. We move through space, and time passes. The two feel like different categories, but near a massive object, this separation breaks down. Space and time become deeply intertwined. Paths through space are also paths through time. The way space is curved affects how time flows. This is not just a poetic idea. It is a precise mathematical relationship that has been tested and confirmed in many experiments and observations. Near a supermassive black hole, this relationship becomes impossible to ignore. The curvature of space-time is so strong that it dominates everything else. Light bends around the black hole, orbits become distorted, and time itself stretches and warps. This leads to another intriguing idea, one that has been explored both in physics and in more imaginative contexts. The idea that near a black hole you could in principle experience a very different passage of time compared to the rest of the universe. If you were able to orbit a black hole at a safe distance, in a region where gravitational time dilation is significant but not destructive, you could experience time more slowly than people far away. When you eventually returned, you might find that much more time had passed for them than for you. This is similar in spirit to the time dilation experienced by fast-moving astronauts, but driven primarily by gravity rather than speed. Of course, this is a thought experiment. The practical challenges of surviving near a black hole, finding a stable orbit, and returning safely make it more a subject for theoretical discussion than for real-world planning. Still, the idea itself is a useful way of illustrating how different the flow of time can become in extreme environments. There is also a deeper question that arises when you think about time near a black hole. What happens to the concept of before and after at the event horizon? For an outside observer, the event horizon appears to be a kind of frozen boundary. Objects seem to slow down and never quite cross it. For an infalling observer, the horizon is just another point along their path. They cross it and continue inward. This difference in perspectives leads to questions about how to define events and their order in time. In general relativity, what one observer considers to be now may not match what another observer considers to be now, especially in strongly curved space-time. This challenges the idea of a single, universal present moment. Near a black hole, the notion of a shared now becomes even more difficult to maintain. From a broader point of view, this connects to philosophical questions about the nature of time itself. Is time something that flows, or is it something that simply exists as part of a larger structure? Does the universe have a single timeline, or many overlapping, observer-dependent ones? Black holes do not answer these questions directly, but they bring them into sharper focus. Now, let us consider how all of this fits into the story of the largest black holes we know. When astronomers study distant quasars and estimate the masses of their central black holes, they're not just measuring mass and light. They're also indirectly probing the structure of space-time in some of the most extreme environments in the universe. The light that reaches us from these regions has been shaped by strong gravitational fields and high-speed motion. It carries the imprint of time dilation and space-time curvature. By decoding these imprints, scientists can test the predictions of general relativity on scales far beyond anything that can be created in a laboratory on Earth. So, in a sense, the largest black holes are not just objects to be measured. They are natural experiments, places where the fundamental nature of time and space is put on display. There is also a quieter, more reflective way to think about this. When you imagine time slowing down near a black hole, it can invite a different perspective on your own experience of time. In daily life, time often feels like something that rushes by. Days blur into weeks, weeks into months. There is a sense of constant forward motion, the idea that time can stretch, slow, and behave differently depending on where you are and how you move can soften that feeling. It suggests that time is not a rigid conveyor belt but a more flexible dimension, one that can be experienced in many ways. Of course, on Earth, these differences are too small to notice without precise instruments. Your personal sense of time is shaped far more by attention, emotion, and memory than by gravity. Still, there is something quietly grounding about knowing that time itself is part of the physical world, subject to the same laws and variations as everything else. Now, let us turn back to the environment near a supermassive black hole and think about what this means for the matter that lives there. Gas and dust in the accretion disk experience intense gravitational time dilation. From a distant point of view, processes in the disk appear to unfold more slowly. Yet from the local point of view, things can be happening very quickly, with violent collisions, rapid heating, and dynamic flows. This difference in perspectives adds complexity to how we interpret observations. A flare in brightness that appears to last a certain amount of time to us may correspond to a different duration in the local frame of the gas that produced it. Astronomers take these effects into account when building models of accretion disks and black hole environments. They use the principles of relativity to translate between what is observed and what is happening locally. This is another example of how time near a massive object is not just a theoretical curiosity. It plays a practical role in how scientists understand real data. There is also an important connection between time and the ultimate fate of matter that crosses the event horizon. From the point of view of an infalling object, there is a finite amount of time between crossing the horizon and reaching the central region of the black hole. What happens there is still a subject of intense research and debate. The known laws of physics, as we understand them, reach their limits. From the outside, that same object appears to be frozen at the horizon, its image fading away but never quite disappearing completely. This duality of descriptions is one of the reasons black holes are so fascinating. They force us to confront the idea that different observers can have very different, yet equally valid accounts of the same event. Time is not just a background for the universe. It is woven into the structure of space itself, shaped by mass and motion, and revealed most clearly in the quiet, powerful presence of the heaviest objects we know. Beyond the comfortable idea that every record eventually stands unchallenged, there lies a more open question that the universe seems to enjoy asking again and again. Is there a true upper limit to how big something can become, or is every largest simply a temporary title, waiting for a future discovery to gently take it away? When it comes to black holes, and especially the immense one we have been circling in our thoughts, this question takes on a special weight. Could anything ever outgrow it? Or are we already brushing up against a kind of cosmic ceiling? To begin exploring this, it helps to step back and look at the universe not as a collection of isolated objects, but as a system in motion. Matter flows, space expands, structures form, interact, and sometimes dissolve. Black holes are part of this system, not exceptions to it. Their growth depends on what the universe around them is doing. At a basic level, a black hole can only grow if there is something available for it to take in. That something might be gas, dust, stars, or even other black holes. All of these sources of mass come from the surrounding environment, which is shaped by the larger patterns of cosmic structure. In the early universe, conditions were especially favourable for growth. Galaxies were closer together, gas was more abundant, collisions and mergers were more common. This created a kind of busy, crowded environment where black holes had many opportunities to gain mass. As the universe has expanded and aged, those conditions have changed. Galaxies are, on average, farther apart. Much of the gas that could form new stars or feed black holes has either been used up or heated to the point where it does not easily collapse. The overall pace of growth has slowed. This shift in cosmic conditions suggests one possible answer to the question of limits. There may not be a hard, absolute maximum size written into the laws of physics, but there may be practical limits set by the way the universe evolves. Think of it like building a structure in a city. In the early days, when land is plentiful and resources are flowing, it is easy to expand. As the city grows and space becomes crowded, expansion becomes more difficult. There is not a law of nature that says you cannot build higher or wider, but the practical challenges increase. For black holes, the resources are mass and time. The larger a black hole becomes, the more mass it needs to grow even larger. At the same time, the universe is spreading out, making it harder for that mass to find its way to the black hole. Now, let us look more closely at one of the key factors that sets a pace for growth, the balance between gravity pulling material in and energy pushing it away. When a black hole feeds, the accretion disk around it can become extremely bright. The radiation produced by this disk exerts pressure on the incoming gas. If the black hole tries to eat too quickly, this outward pressure can push material away, slowing the inflow. This balance defines a kind of natural speed limit for growth, often referred to as the Eddington limit. It does not say how big a black hole can become, but it does say how fast it can grow under steady conditions. Over long periods of time, even growth at this maximum rate can produce very large black holes. But it still requires a steady supply of material and a stable environment. This brings us to another important factor, the structure of galaxies and galaxy clusters. The largest black holes we know of tend to live in the largest galaxies, often at the centres of massive clusters. These are places where gravity has drawn together enormous amounts of matter. Smaller galaxies fall in, merge and contribute their stars, gas and central black holes to the growing system. In this sense, the growth of the largest black holes is tied to the growth of the largest cosmic structures. If there is a limit to how large galaxy clusters can become, or to how much matter can be concentrated in one place, then that may also place an indirect limit on black hole growth. Now let us consider the role of dark matter in this picture. Dark matter does not interact with light, but it does interact with gravity. It makes up a large fraction of the mass in galaxies and clusters. It forms a kind of invisible scaffold that helps shape where ordinary matter collects. However, dark matter does not easily fall into black holes, at least not in the same way that gas and stars do. It does not clump and cool. It does not form disks. It tends to pass through and around other structures. This means that even in regions with a lot of dark matter, the black hole's growth still depends primarily on ordinary matter, the kind that can lose energy and spiral inward. As the universe evolves, and ordinary matter becomes more spread out and more locked up in long-lived stars or hot, diffuse gas, the pool of material that can easily feed a black hole may shrink. This is another way in which practical limits can emerge, not from a fundamental rule, but from changing conditions. There is also the question of stability. As black holes grow, they can become more influential in shaping their surroundings. The energy they release during active phases can heat or expel gas from the central regions of their host galaxies. This can reduce the amount of material available for further growth. In extreme cases, a very active black hole can effectively starve itself by driving away its own food source. This feedback loop can act as a kind of self-regulating mechanism. The black hole grows, becomes more active, pushes material away, and then enters a quieter phase until more material drifts in. Over long periods, this can lead to an equilibrium where the black hole and the galaxy settle into a balance that limits further rapid growth. Now, let us turn to a more speculative angle, one that looks beyond the current universe. If the universe were to remain as it is now, expanding and becoming more diffuse, then the opportunities for black holes to grow larger would continue to decline. In the far future, galaxies will be more isolated, mergers will be rare, gas will be scarce. In such a universe, the largest black holes that exist at that time may simply persist, slowly and quietly, without much further change. However, some cosmological models suggest different long-term possibilities. If, for example, the expansion of the universe were to slow or reverse in the very distant future, then matter could begin to fall back together on large scales. In such a scenario, black holes might once again find themselves in environments rich with material and mergers. This is highly speculative and depends on the overall behaviour of the universe, which is still an open area of research. But it highlights an important point. The ultimate limits on black hole growth may be tied not just to local physics, but to the fate of the universe as a whole. Now, let us bring this back to the present, and to the objects we can actually observe. At the moment, the largest known black holes, like the one associated with the distant quasar we have discussed, sit at the top of the observed range. They weigh tens of billions of suns. They live in massive galaxies, often in dense cosmic environments. Could there be even larger ones out there? It is entirely possible. Our view of the universe is limited by the sensitivity of our instruments and the range of wavelengths we can observe. There may be black holes hidden in regions that are difficult to study, perhaps shrouded by dust or located in parts of the sky that have not been surveyed in detail. There may also be black holes that are not currently active. Without a bright accretion disk, they would be much harder to detect, especially at great distances. This means that the title of largest known is always provisional. It reflects what we have been able to find, not necessarily what exists. As telescopes improve and surveys become more comprehensive, new candidates may emerge. Each one will add another data point, another example of how far black hole growth can go. There is also an interesting connection here to the limits of our measurement techniques. Estimating the mass of a black hole involves indirect methods and models. At very high masses, small uncertainties in measurements can translate into large uncertainties in the final number. This makes it challenging to draw sharp lines between categories like very large and largest. Two black holes might have estimated masses that differ by several billion suns, but their uncertainty ranges could overlap. In such cases, it becomes difficult to say with confidence which one is truly larger. This adds a layer of humility to the whole enterprise. Our knowledge is not just about what is out there. It is also about how well we can measure and interpret what we see. Now let us consider a more fundamental question. Is there anything in the laws of physics that forbids a black hole from becoming arbitrarily large? As far as current theory goes, there is no simple, built-in maximum mass for a black hole. General relativity allows for black holes of any mass, from tiny ones formed in the early universe to enormous ones formed by the merging of galaxies and the steady accretion of matter. However, general relativity does not exist in isolation. It is part of a larger framework of physics that includes quantum mechanics, thermodynamics, and cosmology. When these different areas intersect, new constraints can emerge. For example, black holes are associated with a kind of temperature and entropy. They are not completely isolated from the rest of the universe. Over extremely long timescales, they are expected to slowly lose mass through a process known as Hawking radiation, a quantum effect that allows black holes to emit a tiny amount of energy. For small black holes, this process can be significant. For supermassive black holes, the effect is so slow that it is essentially negligible on timescales comparable to the current age of the universe. But in the very distant future, long after stars have burned out and galaxies have faded, this slow evaporation could become an important part of the story. This introduces a different kind of limit, not on how big a black hole can get, but on how long it can last. In that far future, the universe may be a very different place. Black holes may be among the last large structured objects to exist, slowly releasing their mass back into the universe as faint radiation. This long-term perspective can make the question of largest feel a little different. In the grand sweep of cosmic time, even the most massive black hole is a temporary feature, a phase in the ongoing evolution of the universe. Now let us return to a more immediate observational perspective. When scientists look at the distribution of black hole masses across different galaxies and cosmic times, they see patterns. There are many small black holes, fewer medium ones, and very few at the extreme high end. This suggests that the conditions needed to build a truly enormous black hole are rare. They require the right combination of early formation, rich environment, frequent mergers, and long-term stability. In that sense, the largest black holes are not just big by accident. They are the products of very specific and uncommon histories. This rarity itself can act as a kind of limit. Even if the laws of physics allow for arbitrarily large black holes, the universe may not often provide the right conditions for them to form. There is also an element of chance involved. Small differences in initial conditions, in the density of gas, in the timing of emergers, can lead to very different outcomes. Two seed black holes formed at roughly the same time might follow very different paths, one growing into a modest supermassive black hole, the other becoming an ultramassive giant. This sensitivity to history means that the population of black holes we see today is shaped by a complex interplay of factors, not just simple rules. As you sit with this, you might notice how the question of limits starts to blur into a question of stories. Each large black hole has a story, a path through the history of the universe that led it to its current state. Some stories lead to modest endings, a few lead to extraordinary ones. The idea that something might outgrow the largest known black hole is, in a way, the idea that there might be an even more remarkable story out there, one that began under even more favourable conditions and followed an even more unusual path. This is part of what keeps astronomers searching. The universe has a way of surprising us, of revealing objects and phenomena that push beyond what we thought was possible. Now let us consider one final angle, one that brings the discussion back to a more human scale. When we talk about largest, we're using a concept that matters to us. We like to rank, compare, and categorize. The universe itself does not care about records. It simply unfolds according to its laws and conditions. From that perspective, whether or not anything ever outgrows the largest known black hole is less important than what the search itself reveals. Each new measurement, each new discovery, teaches us something about how matter, gravity, and time interact on the grandest scales. It helps us refine our understanding of the universe we inhabit. Largest is not a final word, but a snapshot in an ongoing journey. The universe is still unfolding, still changing, and still offering new possibilities for what might exist beyond the edges of our current understanding. In the broad sweep of everything that exists, there is a quiet pattern that shows up again and again. Simple rules, applied patiently and without exception, can give rise to outcomes that feel anything but simple. A few basic forces, acting over vast distances and long stretches of time, can build structures that seem to sit at the very edge of what feels possible. This is the deeper context in which the largest black holes, the heaviest galaxies, and the most extreme objects in the universe take shape. They are not accidents or special cases carved out by unique laws. They are the natural results of the same principles that govern falling rain, drifting clouds, and the slow turning of planets around stars. To understand why the universe allows such extremes to exist, it helps to step away from the idea of permission or intention, and instead think in terms of opportunity and consequence. The universe does not choose to make something enormous. It follows its rules, and sometimes those rules, when given enough room and time, lead to outcomes that feel extraordinary to the minds observing them. At the foundation of this story is gravity, a force that is both simple and relentless. Unlike many other forces in nature, gravity does not cancel itself out. There is no negative mass to balance positive mass. Every bit of matter adds to the overall pull. This means that as soon as matter begins to clump, even slightly, gravity starts to amplify that clumping. Denser regions pull in more material, which makes them denser still, which increases their pull even further. This feedback loop is one of the main engines behind the formation of structure in the universe. In the early universe, matter was spread out almost evenly, with only tiny variations in density. Those tiny differences were enough. Over millions and billions of years, gravity took those small irregularities and turned them into galaxies, clusters of galaxies, and the vast web-like patterns of matter that stretch across the observable cosmos. Within that same process, stars formed, lived out their lives, and in some cases collapsed into black holes. The largest black holes, then, are not separate from this story. They are embedded in it. They represent one of the most extreme outcomes of gravity's tendency to gather and concentrate mass. Another important piece of this puzzle is the way the universe expands. Space itself is stretching, carrying galaxies away from each other over time. This expansion might seem like it would work against the formation of large structures, and on the larger scales, it does. There are regions of the universe that will never interact with each other because space between them is growing too quickly. But on smaller, local scales, gravity can overcome expansion. Within galaxy clusters and groups, the mutual pull of matter is strong enough to keep things bound together. In these regions, matter can continue to fall inward, merge, and build larger and larger systems. This balance between expansion and attraction creates a kind of cosmic landscape. Some areas become quiet and diffuse, others become crowded and active. It is in the crowded regions where matter has been drawn together over long periods that the largest galaxies and the largest black holes tend to form. So one reason the universe allows such extremes is simply that it provides the conditions where they can emerge. The combination of gravity's tendency to clump matter and the uneven distribution of that matter across space creates pockets of opportunity for extreme growth. There is also the role of time. The universe is old. 13 billion years may sound like an abstract number, but it represents an immense span of change and accumulation. Processes that would seem impossibly slow on human timescales become powerful when given billions of years to operate. A black hole does not need to grow quickly to become enormous. It needs to grow steadily. A small amount of mass added year after year, century after century, million after million, can eventually lead to something vast. This long-term perspective is essential. The largest black holes are not the result of a single dramatic event. They are the outcome of countless small events layered on top of each other over cosmic time. Each star that falls in, each cloud of gas that spirals inward, each merger with another black hole adds another chapter to a very long story. In that sense, the universe allows extremes because it allows patience. It allows processes to unfold without a built-in endpoint or a forced conclusion. Now, let us turn to another factor, one that is less obvious but just as important: the variety of environments in the universe. Not all regions of space are the same. Some are relatively empty, with galaxies scattered far apart. Others are dense, with hundreds or thousands of galaxies bound together in clusters. These different environments lead to very different evolutionary paths. In a quiet, isolated region, a galaxy may go through a fairly gentle life. It forms stars, uses up its gas, and evolves slowly. Its central black hole may grow to a modest size and then settle into a long, quiet phase. In a crowded cluster, the story is more dynamic. Galaxies interact and merge. Gas is stripped, heated, and redistributed. Central regions become busy crossroads where matter flows inward from many directions. These are the places where black holes can grow most dramatically. They have access to a steady supply of material and frequent opportunities to merge with other black holes. So the universe allows extremes in part because it creates extremes of environment. It does not distribute matter evenly. It builds contrast into its own structure, and those contrasts lead to a wide range of outcomes. There is also a deeper, more abstract layer to this, one that has to do with the laws of physics themselves. The same set of physical laws that allow atoms to form, stars to shine, and planets to orbit also allow black holes to exist and to grow. There is nothing in those laws that draws a clear line and says, beyond this point, mass cannot be concentrated any further. Instead, there are conditions and balances. Pressure can counter gravity. Energy can push back against collapse. But if gravity is strong enough, and if other forces are not able to resist, then collapse can continue. This is why black holes exist in the first place. They represent a regime where gravity overwhelms other forces. On larger scales, similar ideas apply. There is nothing in the laws of physics that forbids a galaxy from becoming very large, or a cluster of galaxies from becoming very massive. There are practical limits imposed by the expansion of the universe and the availability of matter, but those limits are not sharp, fixed boundaries. This open-endedness is part of what makes the universe feel so rich and varied. It does not funnel everything toward a single uniform outcome. It allows a wide spectrum of structures to exist, from small, faint dwarf galaxies to giant ellipticals, from modest black holes to ultramassive ones. There is also the role of randomness. The early universe was not perfectly smooth. It had tiny fluctuations in density, likely seeded by processes that occurred in the first moments after the Big Bang. Those fluctuations were essentially random, within certain statistical patterns. Over time, gravity amplified those initial differences. Regions that started out just slightly denser ended up becoming the sites of galaxies and clusters. Regions that were slightly less dense became vast cosmic voids. This means that the universe's structure today carries a kind of imprint of those early, almost imperceptible variations. The largest black holes we see may owe their existence, in part, to being born in just the right place within that initial pattern. This introduces an element of chance into the story. Not everything about the universe's extremes is dictated by simple, deterministic rules. Some outcomes depend on where and when something happens within a complex, evolving system. Now, let us consider another angle, one that connects the existence of extremes to the idea of stability. In many systems, extremes can play a stabilizing role. This might sound counterintuitive, but it shows up in different areas of science. In galaxies, for example, a very massive central black hole can help regulate the flow of gas and the rate of star formation. By releasing energy during active phases, it can prevent the galaxy from forming too many stars too quickly, which might otherwise deplete its gas and lead to a rapid, unbalanced evolution. On larger scales, clusters of galaxies and their massive components help shape the motion of surrounding matter, contributing to the overall structure of the cosmic web. From this perspective, the largest black holes are not just extreme outliers. They are part of a system of checks and balances that influences how the universe evolves. This does not mean that the universe needs them in any purposeful sense, but it does mean that their existence is woven into the broader dynamics of cosmic structure. There is also a thermodynamic angle to consider. The universe as a whole tends towards states of higher entropy, which is often described as a measure of disorder, or the number of ways a system can be arranged. Black holes are associated with very high entropy. In fact, for a given amount of mass, a black hole has more entropy than almost any other object you can imagine. This has led some physicists to think of black holes as natural endpoints for the concentration of matter and information. They represent a kind of extreme state in the universe's tendency to explore all possible configurations. From this viewpoint, the existence of very large black holes is not surprising. It is a reflection of the universe's underlying drive towards states that maximize certain physical quantities, like entropy, under the constraints of its laws. This is a deep and still developing area of research, but it highlights another way in which extremes can arise naturally, not as anomalies, but as favored outcomes under certain conditions. Now, let us bring this discussion back to a more grounded observational level. When astronomers look at the distribution of black hole masses across the universe, they see a wide range, not a single dominant size. There are many small black holes, fewer medium ones, and very few at the high end. This kind of distribution is common in nature. It shows up in the sizes of earthquakes, the brightness of stars, and the wealth of cities. Such patterns often emerge from systems where growth is driven by a combination of steady processes and occasional, large, random events. In the case of black holes, the steady process is accretion. The large, random events are mergers. This combination naturally produces a few very large outcomes and many smaller ones. It is another example of how extremes can arise without needing special rules to create them. As you sit with these ideas, you might notice how they shift the meaning of the word allow. The universe does not allow extremes in the sense of granting permission. It allows them in the sense that it does not prevent them. Its laws are open-ended enough, its timescales long enough, and its environments varied enough that a wide range of outcomes can emerge. This openness is part of what makes the universe such a rich place to study. It is not a tightly constrained system that produces the same results everywhere. It is a landscape of possibilities shaped by simple rules and complex histories. There is also a more reflective way to look at this. The fact that the universe can produce something as vast and heavy as the largest black holes, and also something as delicate and fleeting as a human thought, speaks to the breadth of scales and experiences it contains. Both exist within the same set of physical laws. This can be a quiet source of connection. When you think about extremes in the universe, you're not just thinking about distant objects. You're thinking about the range of what is possible within the reality you inhabit. Now, let us consider how this understanding shapes the way scientists approach their work. Knowing that extremes can and do exist encourages astronomers to keep looking beyond the familiar. It motivates deeper surveys, more sensitive instruments, and more ambitious models. The possibility that something even larger or more extreme might be out there is a powerful driver of exploration. At the same time, studying these extremes helps refine our understanding of the laws that govern everything else. If a theory can explain both the ordinary and the extraordinary, it gains strength. If it fails at the extremes, it points to where new ideas may be needed. In this way, the largest black holes are not just impressive objects, they are tests of our understanding, markers of how far our theories can reach. The universe is not a place of narrow limits, but a place of broad possibilities, where simple rules, given enough space and time, can unfold into outcomes that quietly stretch the edges of what we can imagine. In the wide conversation between matter and motion that has been unfolding since the universe was young, there are a few participants whose voices carry farther than most. The largest black holes, those immense concentrations of mass tucked into the hearts of galaxies, are among them. They do not speak in sound or light of their own, but in influence. Their presence shapes the paths of stars, the flow of gas, and the long-term stories of the galaxies that host them. And, in a more subtle way, they also shape how we, as observers, think about our own place in the cosmos. To begin easing into this, let us start with the most immediate level of impact, the relationship between a giant black hole and its host galaxy. A galaxy is not a static object. It is a living system in the sense that it changes, grows, and reorganizes itself over time. Stars are born in clouds of cold gas. Those stars live, shine, and eventually die, returning material to the surrounding space. Gas flows along spiral arms, drifts toward the center, and is sometimes pushed back out again by energetic events. Over billions of years, the overall shape and character of the galaxy can shift. At the center of many of these systems, the largest black holes act as a kind of regulator, not a ruler that dictates every detail, but a presence that can tip the balance in certain directions. When a central black hole is quiet, gas in the galaxy can cool and settle into the kinds of dense clouds that form new stars. Spiral arms can light up with bright young clusters. The galaxy can take on a lively, active character, with ongoing cycles of birth and death among its stellar population. When that same black hole becomes active, the picture can change. As material falls into the black hole's accretion disk, the energy released can be enormous. Radiation pours out. High-speed jets of particles can be launched along the black hole's rotational axis. These outflows interact with the surrounding gas, heating it, and sometimes driving it away from the central regions. Hot gas does not collapse easily into new stars. If enough of the gas in a galaxy is heated or expelled, star formation can slow down or even pause for long periods. This process is often described as a kind of feedback loop. The galaxy provides the black hole with material. The black hole, in turn, releases energy that affects how much material the galaxy can use to form new stars. Over time, this interaction can help set the overall pace of the galaxy's evolution. In galaxies that host the largest black holes, this feedback can be especially powerful. The energy involved is so great that it can influence gas not just in the immediate centre, but across much of the galaxy and even into the surrounding intergalactic space. Observations of massive galaxies and clusters often reveal large bubbles or cavities in the hot gas that fills the space between galaxies. These structures are thought to be carved out by past activity from central black holes, their jets pushing aside vast amounts of material. This suggests that the influence of these giants extends well beyond the visible stars and into the larger environment of galaxy clusters. Now, let us move one step outward, from galaxies to stars. On a local scale, near the very centre of a galaxy, the gravitational influence of a supermassive black hole can shape the orbits of stars in dramatic ways. Stars can move at incredible speeds, following elongated, looping paths that bring them close to the central region, before flinging them back out again. In some cases, a star's orbit can bring it too close. When a star passes within a certain distance of a black hole, the difference in gravitational pull between the near side and the far side of the star can become so great that the star is pulled apart. This process is known as a tidal disruption event. As the star is stretched and torn, some of its material falls into the black hole, forming a temporary accretion disk. This disk can flare brightly, producing a burst of light that can be seen across vast distances. These events are relatively rare, but when they happen, they offer astronomers a chance to watch a black hole in the act of consuming a star, a process that reveals details about the black hole's mass and spin. For the stars themselves, this is an endpoint, a dramatic conclusion to a long journey through space. For the galaxy, it is a small, localized event, one part of a much larger ongoing story. Now, consider the broader population of stars in a galaxy with a very large black hole. If the black hole's activity suppresses star formation for long periods, the galaxy can become dominated by older, redder stars. These stars are cooler and longer-lived, and their light gives the galaxy a more subdued, uniform appearance. This is often the case for massive elliptical galaxies at the centres of clusters. They host some of the largest known black holes and have relatively little ongoing star formation. Their stellar populations are old, and their structure is smooth and rounded rather than rich in spiral features. In contrast, galaxies with smaller or quieter central black holes may continue forming stars for much longer, maintaining a more varied and dynamic appearance. This connection between black hole activity and stellar populations is one of the ways astronomers link the small-scale physics of accretion disks to the large-scale appearance of galaxies. Now, let us take another step outward, from stars and galaxies to the larger cosmic web. Galaxies are not scattered randomly through space. They are arranged in a vast network of filaments, clusters, and voids. This structure emerged from the growth of tiny density variations in the early universe, amplified by gravity over billions of years. The largest black holes tend to be found in the densest parts of this network, at the centres of the most massive galaxies in the largest clusters. These regions are crossroads where matter has been flowing in from many directions for a very long time. In this sense, the presence of an ultra-massive black hole can be seen as a marker of a particularly rich and active part of the cosmic web. It tells a story about where matter has accumulated and how the large-scale structure of the universe has evolved. This means that when astronomers study the biggest black holes, They are not just learning about those objects themselves, they're also learning about the environments in which they formed and about the history of structure formation on the larger scales. Now let us shift the focus a little and consider what all of this means for us, here on a small planet orbiting an ordinary star in a fairly typical galaxy. At first glance, the connection might seem distant. The largest black holes are billions of light years away. Their gravity does not reach us. Their activity does not affect our solar system. In practical terms, our daily lives are untouched by their presence, and yet there is a deeper, more indirect connection. The same processes that allow these giants to exist also shape the universe that made our galaxy, our star and our planet possible. The elements that make up your body were forged in stars that lived and died long before the sun was born. Those stars formed in galaxies that evolved under the influence of their own central black holes and their place in the cosmic web. In this way, the story of the largest black holes is part of the larger story of cosmic history, a history that eventually led to the conditions in which life could emerge. There is also a connection at the level of understanding. When we study extreme objects, we test the limits of our theories. The physics that describes black holes also describes the behavior of gravity in more familiar settings. By seeing how well our models work in the most extreme environments, we gain confidence in their application closer to home. For example, the same theory of gravity that predicts time dilation near a black hole also underlies the calculations that allow GPS satellites to function accurately. The connection between the very large and the very practical runs through the mathematics of space and time. In that sense, learning about the largest black holes is not just an abstract exercise. It feeds back into our broader understanding of how the universe works at all scales. Now, let us take a moment to reflect on the human side of this exploration. Throughout history, people have looked up at the night sky and wondered about what lies beyond. Early observers mapped the motions of stars and planets, often weaving them into stories and myths. Over time, those stories gave way to measurements, theories, and instruments. Today, when astronomers talk about black holes weighing billions of suns and sitting billions of light years away, they are participating in a very long tradition of curiosity, one that has grown in scope and precision over thousands of years. There is something quietly remarkable about the fact that a species that evolved on a small rocky planet can build tools and ideas that reach so far beyond its immediate surroundings. This perspective can shift how you think about us in the phrase galaxies, stars, and us. We are not separate from the universe we study. We are part of it, made of the same kinds of matter, governed by the same physical laws. Our ability to reflect on these giants of gravity is itself a product of the long chain of cosmic events that include star formation, galaxy evolution, and the growth of black holes. Now, let us return to the idea of meaning, not in a philosophical or emotional sense, but in a scientific one. In science, to say that something means something often means that it provides information. It tells us something about the system it's part of. The largest black holes tell us about the conditions of the early universe, about the environments in which galaxies formed, and about the processes that can concentrate matter on extreme scales. They also tell us about the limits of our current theories. Where our models work, they are confirmed. Where they struggle, they point toward areas where new ideas may be needed. This makes these giants important not just as objects of study, but as guides for future research. There is also a more subtle meaning that comes from the way these objects stretch our imagination. Thinking about something that outweighs billions of stars and bends time itself can make everyday concerns feel smaller, at least for a moment. It can create a sense of perspective, a reminder that the world we experience is part of a much larger whole. This does not make personal experiences less important. It simply places them within a wider context. Now, let us consider how these ideas might connect to the future of exploration. As telescopes become more powerful and new technologies come online, astronomers will be able to study black holes and their environments in greater detail. They will be able to observe the earliest quasars, map the motions of gas and stars in distant galaxies, and perhaps even detect the gravitational waves from merging supermassive black holes. Each of these advances will add new layers to our understanding of how these giants interact with their surroundings. This ongoing process is itself a kind of story, one that unfolds over generations of scientists and observers. In this story, each discovery builds on the work of those who came before, refining and sometimes overturning earlier ideas. The largest black holes, by pushing the boundaries of what is possible, often play a central role in these moments of change. Now, let us return one last time to the image of a galaxy built around a darkness at its heart. From a distance, a galaxy can look like a simple, beautiful pattern of light, spiral arms, glowing cores, scattered points of brilliance, but at the centre of that pattern, there is often something that cannot be seen directly, something that shapes the whole without ever appearing in the picture. This can be a quiet reminder that not everything important is visible, and that some of the most influential parts of a system work behind the scenes. The largest black holes are not isolated curiosities. They are woven into a vast network of relationships, linking the fate of galaxies, the lives of stars, and the unfolding of human curiosity into a single, continuous tapestry of cosmic history. Long after the last bright spirals of young stars have faded into softer, older glows, the universe will continue its slow, patient unfolding. The largest black holes, those immense anchors of gravity that once sat at the centres of bustling galaxies, will still be there, not as dramatic engines of light and motion, but as quiet presences in a cosmos that has grown calmer and more spread out. Their future is not one of sudden endings or violent transformations, but of gradual change stretched across spans of time so long that ordinary words like century and era lose their familiar meaning. To ease into this distant horizon, it helps to think about how the universe itself is changing. Right now, galaxies are still forming stars, merging with one another and reshaping their structures. Gas clouds drift, collapse, and ignite. Black holes feed, flare, and sometimes go quiet again. But over very long timescales, the overall trend is toward a slower, more diffuse universe. Space continues to expand. Galaxies that are not bound together by gravity move farther and farther apart. The dense regions where matter once gathered become more isolated islands in a growing sea of emptiness. In this future, the largest black holes will remain at the centres of their galaxies, but those galaxies themselves will be more solitary. Mergers will become rare. Fresh supplies of cold gas will be harder to come by. The busy, interactive environment that once helped black holes grow into giants will gradually fade away. This shift in surroundings will change the role these black holes play. During their active phases, black holes can be some of the brightest objects in the universe. Their accretion disks glow, their jets carve paths through surrounding space, and their energy shapes the fate of nearby gas and stars. In a quieter universe, those dramatic displays will become less common. Without a steady flow of new material, the accretion disks will thin out. The bright quasar-like phases will end. The black holes will settle into long periods of relative stillness, fed only by the occasional wandering star or stray cloud of dust. From the outside, they will appear as dark, massive points at the centres of galaxies that themselves have grown dimmer and older. Now let us take a closer look at what will be happening to the galaxies around them during this time. Stars do not last forever. The most massive ones burn brightly and die quickly. Smaller stars, like red dwarfs, can shine for trillions of years, far longer than the current age of the universe. But even these long-lived stars will eventually exhaust their fuel. As the universe ages, the population of bright young stars will dwindle. Galaxies will become dominated by older, cooler stars. Their light will shift toward the red end of the spectrum. The vibrant blues and whites of active star-forming regions will fade. In this era, often referred to as the Degenerate era in cosmological models, the universe will be populated mostly by remnants. White dwarfs, neutron stars, black holes, and faint, long-lived stars will make up most of the visible mass. The largest black holes will be among the most massive and stable objects in this future universe. They will outlast stars, planets, and even galaxies as we know them. There is a certain quiet symmetry in this. Black holes are born from the collapse of stars, and in the far future they may be among the last things standing, long after the era of star formation has passed. But even black holes are not truly eternal. According to our current understanding of physics, black holes are not completely isolated from the rest of the universe. They are associated with a very faint form of radiation, known as Hawking radiation, which allows them to slowly lose mass over extremely long periods of time. This effect is incredibly weak for large black holes. For a black hole with the mass of the Sun, the time it would take to evaporate completely through this process is far longer than the current age of the universe. For a supermassive or ultramassive black hole, the timescale is unimaginably longer, on the order of 10 to the power of 100 years or more. These numbers are so large that they are difficult to put into any meaningful context. They extend far beyond the lifetimes of stars, galaxies, and even most cosmological models. Still, the implication is profound. Given enough time, even the largest black holes will slowly fade away, releasing their mass back into the universe as a trickle of low-energy radiation. This introduces a very different kind of future, one not dominated by growth and accumulation, but by gradual dispersal. Now, let us imagine what the universe might look like during this extremely distant era. Galaxies will have drifted far apart, separated by vast, empty regions of space. The cosmic web that once connected them will have stretched and thinned. The night skies of any remaining observers, if such a concept still makes sense, would be mostly dark. Within isolated galaxies or galaxy remnants, black holes will remain as central features. They will be among the few objects still capable of interacting with their surroundings in any significant way. Occasionally a star or a compact object might wander too close and be drawn in, providing a brief, faint flare of energy. These events will be rare, separated by enormous spans of time. Most of the time, the black holes will simply sit, their presence marked only by the motion of whatever faint objects still orbit them. In this future, the idea of a largest black hole may lose much of its meaning. With so little interaction between galaxies, the relative sizes of black holes will change very slowly, if at all. The giants that exist at that time will likely remain the giants for the remainder of the universe's active life. There is also a more speculative aspect to this story, one that depends on the ultimate fate of the universe itself. Our current understanding suggests that the expansion of the universe is accelerating, driven by something we call dark energy. If this continues indefinitely, the universe will grow colder and more isolated over time, leading to a future sometimes described as heat death, where energy is evenly spread out and no useful work can be done. In such a universe, black holes play a central role. They are among the most efficient ways of concentrating energy and entropy. As they slowly evaporate, they release that energy back into the universe, contributing to the overall trend toward equilibrium. In this view, the largest black holes are not just endpoints of growth, they are also part of the long, slow process by which the universe moves toward a more uniform state. Another possibility, still purely theoretical, is that the expansion of the universe might one day slow down or reverse. In a scenario like this, matter could begin to fall back together on large scales, potentially leading to new periods of structure formation and black hole growth. If something like that were to happen, the quiet future we have been describing would be interrupted. The giants of one era might become the seeds of new giants in another. This is a reminder that our picture of the far future is shaped by our current understanding, which is always open to revision as new discoveries are made. Now let us return to a more grounded perspective and think about what these ideas mean in terms of scale and patience. The timescales involved in the quiet future of black holes are so long that they stretch the limits of imagination. Millions of years, billions of years, Even trillions of years are small numbers compared to the timescales associated with black hole evaporation. This can make the whole story feel abstract, disconnected from any kind of experience. And yet, the same laws of physics that govern these distant futures also govern the present moment. The same principles that allow a black hole to slowly lose mass through Hawking radiation also describe the behavior of particles in a laboratory experiment. This connection between the everyday and the extreme is one of the quiet threads that runs through the study of the universe. Now, let us think about the idea of quiet in a more literal sense. Sound, as we know it, requires a medium. It needs air, water, or some other material to carry vibrations. In the deep future universe, with matter spread thinly across vast distances, there will be very little to carry sound. The universe will be, in a literal sense, silent. The largest black holes will exist in this silence, surrounded by enormous regions of near-empty space. Their interactions, when they occur, will be expressed not in sound or light, but in the slow, subtle movements of matter and the even slower trickle of radiation from their evaporation. This picture can feel stark, but it also carries a kind of simplicity. The early universe was busy, hot and crowded. The middle-aged universe, the one we live in now, is rich with structure and activity. The far future may be sparse, cold, and quiet. Each of these phases has its own character, and the largest black holes play different roles in each one. In the early and middle phases, they are builders and regulators, shaping galaxies and influencing star formation. In the far future, they become long-term custodians of mass and energy, slowly releasing what they have gathered over eons. There is also a reflective angle to this story. When we think about the quiet future of black holes, we're thinking about a time far beyond any human horizon. It is a reminder that the universe's story does not revolve around us or our timescales, and yet our ability to imagine and describe such a future is itself part of the universe's unfolding. The thoughts you're having right now about distant times and vast objects are small events in a much larger process. This can lend a certain gentleness to the way we think about both the present and the future. Now, let us return briefly to the idea of interaction. Even in a quiet universe, interactions do not stop entirely. Gravity continues to operate. Objects continue to move, even if very slowly. Black holes continue to influence whatever remains around them. There may be rare encounters between black holes themselves. In regions where galaxies or their remnants are still bound together, black holes could eventually spiral toward one another and merge. Such events would release bursts of gravitational waves, ripples in space-time that travel outward, carrying energy across the universe. In a future where most other forms of energetic activity have faded, these mergers could stand out as some of the last dramatic events on a cosmic scale. Over even longer times, as black holes evaporate, the mass and energy they release will spread out, contributing to the overall background of the universe. This slow diffusion of energy is part of the larger trend toward uniformity that many cosmological models predict. Now, let us bring this back to the idea of meaning, not in a philosophical sense, but in a structural one. The quiet future of the largest black holes shows how the universe moves through different regimes, from growth to stability, from activity to stillness, from concentration to dispersion. Black holes, especially the largest ones, trace this arc in a particularly clear way. They begin as products of collapse and growth. They reach a phase of influence and regulation. They end, if our theories are correct, as sources of slow, steady release. This makes them a kind of thread running through the entire history of the universe, from early structure formation to the far future. They are not just objects in space. They are markers of time, witnesses to vast stretches of cosmic history, and participants in the long transformation of the universe from a hot, dense beginning to a cold, diffuse future. Somewhere between the vast distances we have wandered and the small, familiar space where you're sitting or lying right now, there is a gentle crossing point. It is the place where thoughts about galaxies, black holes, and cosmic time slowly give way to the quiet awareness of your own breathing, the weight of your body, and the steady presence of the world close at hand. This is where we begin to drift back from the edge, carrying with us one last thought, not as a conclusion, but as a soft companion that can linger as the universe fades into the background. Over the course of this slow journey, we have moved through ideas that stretch far beyond everyday experience. We have spoken about gravity gathering matter into stars, stars collapsing into black holes, and black holes growing into giants that shape entire galaxies. We have considered how time itself bends and slows near these massive objects, how light carries messages across billions of years, and how the far future of the universe may be shaped by quiet, patient processes that unfold long after the last bright stars have dimmed. Now, instead of pushing further outward, let us gently turn inward. It can be grounding to notice how different scales of existence sit side by side. On one level, there are black holes weighing billions of suns, influencing regions of space larger than entire solar systems. On another level, there is the simple rhythm of your breath, the subtle movement of air in and out, the quiet beating of your heart. Both of these things exist within the same universe, governed by the same underlying laws. This connection is not just poetic, it is literal. The atoms in your body were forged in stars that lived and died long before the sun was born. Those stars formed in galaxies that grew and evolved under the influence of gravity, dark matter, and in many cases central black holes. The elements that make up your bones, your blood, and your breath were once part of distant, glowing furnaces of nuclear fusion. In that sense, when you think about the largest black holes, you're not thinking about something entirely separate from yourself. You're thinking about a different chapter in the same long story of matter and energy that eventually led to this moment, this place, and this quiet awareness. There is a subtle shift that can happen when you hold this perspective for a while. The universe stops feeling like a distant backdrop and starts to feel more like a shared environment, one that includes everything from the heaviest objects we can imagine to the lightest thoughts that pass through your mind. Now, let us return briefly to the idea of the edge that we have been circling. When we talk about the edge in the context of black holes, we often mean the event horizon, the boundary beyond which information cannot return. It is a line in space that marks a change in what can be known from the outside. It represents a kind of limit, a place where our ability to observe and measure reaches its end. But there are other kinds of edges as well. There is the edge of our current understanding, where theories begin to blur and new ideas are needed. There is the edge of the observable universe, beyond which light has not yet had time to reach us. And there is the edge of personal awareness, the place where focused thought gives way to rest, and attention softens into something quieter and more diffuse. Drifting back from the edge, in this sense, is not about turning away from curiosity. It is about letting curiosity settle into a more comfortable, less demanding form. Instead of asking, what is the largest black hole? Or, how does time behave near it? You might simply let the idea of vastness sit in the background, like a distant horizon that does not need to be reached. There is a calm that can come from knowing that not everything needs to be understood all at once, or even understood at all. The universe is full of details, layers, and depth that no single mind can fully explore, and yet, that does not make our small moments of understanding any less meaningful. In fact, it can make them feel more precious. Think for a moment about how much has to come together for you to be here, listening to these words. A planet needs to form in the right place around a star. That star needs to be part of a stable galaxy. That galaxy needs to exist in a universe with the right balance of forces and constants. The universe itself needs to have unfolded in a way that allows matter to clump, stars to shine, and chemistry to become complex. Each of these steps depends, in some way, on the same fundamental processes we have been talking about: gravity, energy, time, and the flow of matter. The largest black holes are extreme expressions of those processes. You're a much smaller, more delicate expression of them, but both are part of the same system. This does not mean that there is a hidden message or purpose encoded in the universe. It simply means that there is continuity, a thread that runs from the simplest interactions between particles to the grandest structures in space. Now, let us consider the idea of scale one more time, but from a different angle. We often measure things by how big they are, how heavy, how bright, how far away. These are useful ways of organizing our understanding. But there is another way to think about importance, one that is not tied to size or mass. A single, quiet moment of awareness can be just as real, in its own way, as the existence of a black hole at the center of a distant galaxy. They occupy different places in the universe's structure, but neither is more real than the other. This is not a scientific statement so much as a way of holding the experience of being in a universe that contains both extremes. As you let this thought rest, you might notice a sense of balance. The universe is not only about the biggest and the most powerful, it is also about the small, the fleeting, and the subtle. Now, let us gently revisit some of the ideas we have touched on, not to summarize them in a formal way, but to let them drift past like familiar landmarks. We began by thinking about gravity, that simple, persistent tendency for matter to draw together. We followed it as it gathered gas into stars, stars into galaxies, and galaxies into clusters. We watched as some stars collapsed into black holes, and as some black holes grew into giants that shaped their surroundings. We considered how light carries information across vast distances, allowing us to learn about objects billions of years in the past. We explored how time itself slows and stretches in the presence of extreme mass, and how perspective shapes what is seen and what is experienced. We looked ahead to a far future where the universe grows quieter, where the largest black holes remain as long-lived witnesses to a cosmos that has moved beyond its most active phases. Each of these ideas can stand on its own, but together they form a kind of gentle arc, one that moves from beginnings to growth, from activity to stillness. Now, instead of pushing that arc toward a final point, let us allow it to remain open. The universe, after all, is not finished. New stars are still forming, new black holes are still being born, galaxies are still merging and changing shape. Even as we speak, light is leaving distant objects, beginning journeys that will last longer than the entire history of human civilization so far. This ongoing nature of things can be quietly reassuring. It suggests that there is always more happening, more unfolding, beyond the immediate scope of what we can see or think about. There is also something comforting in the idea that the universe does not rush. Its most dramatic processes often take millions or billions of years. Compared to that, our own lives are brief, but that does not make them insignificant. It simply places them within a larger rhythm. As you listen, you might notice your own sense of time shifting slightly. Perhaps the steady flow of words, the unhurried pace of ideas, has softened the feeling of minutes passing. This too is a small echo of the themes we have been exploring. Time, even in the everyday sense, is shaped by attention and experience. Now let us turn to that one last thought mentioned at the beginning, not as a final answer, but as a gentle point to rest on. The thought is this: the universe is not something that exists out there while you exist in here. You are part of it. The same space that holds galaxies and black holes also holds you. The same time that stretches and bends near massive objects also carries your own moments forward. This does not mean that you're influenced in any direct physical way by the largest black holes in the universe. Their gravity does not reach you. Their light, if it does reach you, arrives only after billions of years, long after whatever produced it has changed. But it does mean that, at a deeper level, there is no sharp boundary between the universe and you. There is only one system, one continuous fabric of matter, energy, space, and time, within which everything takes place. Holding that idea does not require you to do anything special. You do not need to draw a conclusion from it or turn it into a belief. You can simply let it be there, like a quiet background note. Now, as we begin to ease away from the grand scale of cosmic giants and back toward the simple, steady presence of this moment, you might notice small details around you. The sound of a room, the feeling of fabric or air on your skin, the gentle rise and fall of your chest. These are not separate from the universe we have been talking about. They're expressions of it, just on a scale that fits comfortably into a single human experience. There is something quietly powerful about that continuity. It means that when you think about a black hole at the centre of a distant galaxy, you are not stepping outside of reality into some abstract realm. You are exploring a different region of the same reality you inhabit right now. As this thought settles, you might feel a sense of both smallness and connection. Smallness, because of the vastness of what lies beyond. Connection, because of the shared foundation beneath it all. Now, let us slow things down even further. There is no need to hold on to every detail we have discussed. You do not need to remember the numbers, the names, or the specific processes. If any particular image or idea stays with you, that is enough. Perhaps it is the image of a galaxy turning slowly around a dark centre, or the idea of time stretching near something immensely heavy, or the thought of light travelling for billions of years just to reach a mirror in a telescope. Or perhaps it is simply the feeling of vastness itself, a sense of open space that does not demand anything from you. You can let the rest fade. As you continue on from here, whether into sleep, rest, or just a quieter state of awareness, the universe does not need to be actively thought about. It will continue to do what it has always done, unfolding at its own pace, building and dissolving structures, carrying light across space, and shaping time around mass and motion. And you, in your own small, immediate way, will continue to be part of that process, breathing, resting, and moving through your own moments. There is no sharp ending to this story, just as there is no sharp ending to the universe's own unfolding. There is only a gentle easing, a soft transition from focused curiosity to a more open, relaxed presence. So for now, let the idea of those distant giants drift into the background. Let the thought of galaxies and black holes become like a far-off horizon, still there, but no longer in the centre of attention. Stay with what is close, what is quiet, and what is easy to hold. The universe in all its vastness will still be there when you next think to look outward again.